Is this really happening?
It is really happening.
Oh my goodness.
Claire, I'm just trying to calm down from the rave that we had, backstage.
Okay, so
It was
I
so
like
good.
the music. An engineer who I think is fabulous sent me a private note in one of the earlier live streams, and he's like, you could do this kind of music instead, and those are great ideas. But I feel like music is very personal, and everybody has a different preference, I guess. And,
Well, I mean, if this is your personal pick, I mean,
You're there?
I want to go to a rave with you. This is good.
It was fun. All right. Well, we are here to welcome everybody to live stream 4 of Posette, an event for Postgres 2026. Do you know what Posette stands for, Flora? I'm putting you on the spot.
Oh my gosh, this feels like an oral exam. Can you please tell me?
Postgres open source ecosystem talks, training, and education.
Whew.
But it's interesting, when we were trying to come up with a name for this event, the inspiration was FOSDEM, because so many people know the name FOSDEM, like 8,000 people go there every year, but most people don't know what all of the letters in the acronym stand for. So it's okay not to know what all the letters. Anyway.
Well, I'm glad that you came up with an acronym, because that's a mouthful,
Posette. It's easy to say. I like it.
Good.
All right. I just realized we don't have our names underneath our faces, so we'll fix that in one of the breaks. But we'll introduce ourselves in just a second. And I will see if I can move the slides. All right. So there are 44 talks in this event this year.
Yeah, you told me this morning or my morning, I guess it's not necessarily your morning, that it's 11 talks per live stream. That's a lot. That's good. Great content.
It is a lot. We had 238 talk proposals submitted this year that we had to wade through in order to come up with the 42 accepted talks. And then, of course, we have the invited keynote. So we are here for live stream 4. If you want to go watch the previous live streams, they're all on YouTube. And we'll give you links later. You can just search online. They're easy to find, too. And actually, all the talks from live streams 1, 2, and 3 are also published individually already on YouTube. Right. So everything's there. But let's focus on live stream 4. And my name's Claire Giordano. I work at Microsoft. I'm actually the organizing chair of this event this year, and was involved in talk selection as well. So I'm very invested in making sure everybody has a good time and learns a lot from this.
Well, thanks for putting another year of such a great event on, Claire. It's really good so far. My name is Floor Drees. I work at EDB, do anything with our open source folks and work in the open source community. And I'm excited to join this live stream.
And it's interesting that I mentioned FOSDEM a second ago, because that is where we first met in person.
Sure. Yeah, you gave me socks. So, we were instant friends, obviously.
Oh my goodness. Okay. So this is all about making really valuable Postgres content available in these 25-minute bite-sized pieces for people to learn from. And you don't need to suffer from jet lag. You don't need to get a travel budget or convince your boss that it's a good use of your time. everything's on YouTube and available. So yeah, that's kind of the mission and the goal. And I think you guys are going to be happy with the talks today. The conference is organized by the Postgres team at Microsoft. So big thank you to a whole team of people. We'll pop their faces up later. And this year, we actually have produced the conference in partnership with AMD. So I do want to say a special thank you to AMD for their support in putting this together this year. And because, as you know, Floor, from organizing conferences, it takes a village, and there's a lot of work involved. And you also need financial support too. So
absolutely, and so many moving pieces always. I do want to call out that we have a code of conduct for this event. We want to make sure that this event is welcoming for everyone to learn. The code of conduct, of course, also applies to Discord, but please do interact on the Discord because we would love to hear from all of you.
Yes. And QR code on them.
Yeah, perfect. Yeah, so thanks for calling that out. There's a QR code on the slide if you want to check out the code of conduct. Also, on all of the pages on the Posette website, you can find the code of conduct in the footer if you want to check what's there. Yeah.
Floor and I know each other well enough that if either one of us misses a main point, the other one's going to point it out, I'm sure. So
that's good.
You can return the favor as we proceed through this deck. Today's live stream has machine-generated captions on YouTube, right?
Yes, and they're, good, but there's actual professional captions for the published talks, and so and they're translated in like 16 different languages, which is an amazing service, really. So just to make all of the content of today and of the previous live streams accessible to everyone.
And I know because of how we all consume like shows on TV, for those of us who watch Netflix or movies or series or something, like a lot of us use captions because even when we speak the language, sometimes we don't understand that person's accent. So there's a whole curb cut effect going with captions. But certainly at Microsoft and many other companies, there's a big commitment to accessibility. So yeah, we're happy to do this.
Love that.
I also, before we dive in, I just want to say thank you to all the speakers. There are 50 speakers who put a lot of energy and shared their expertise as part of this year's event. And you might be thinking 44, 50, 44, but you'll figure it out as we progress, why those numbers don't match exactly. And oh yeah, if you're having trouble figuring out like which of the 44 talks you are going to watch later, because obviously here today we're only going to show 11 of them. We put together this blog post called The Ultimate Guide. You can find it. I'm going to go back. You can find it with that QR code and that short URL, aka.ms/Posette guide. And I don't know. I think the categories and the tags are useful.
Yeah, you group them really well. So yeah, pick and choose.
If you're only interested in developer tools or VS Code or Apache Age or logical decoding, like you can find those talks fairly easily using this thing. And now we need to talk about the virtual hallway track. What in the world is a virtual hallway track, Floor? How do I explain it to someone?
I mean, like if anyone goes to a conference, they know that a hallway track is so valuable, right? That's where you meet people. That's where you build your network. And we just brought it online to Discord. So you need to find the PosetteConf channel on the Microsoft open source Discord, and you can connect with everyone watching at the same time as you are.
And one of the benefits as well is that most of the speakers are there while their talk is being live streamed. So if you have questions for them, don't be shy. Ask the questions. They're there to kind of explain things, and it's just like at an in-person conference when you try to catch them at the end of their talk. Well, now you can catch them in the middle of their talk. So that is, I think, one of the reasons to participate live. Versus watching all of the talks later at your leisure. Well, there are surveys, as always, right? As is tradition with a conference.
Yeah, and Claire, you mentioned like people put a lot of time also in preparing their talks, and so they definitely want to hear from you too. If you have any feedback or suggestions, or maybe suggestions, why not? please make sure that you communicate that to the speakers by filling out the survey, and comment on the event itself as well. Like, what can we do to make this even better next year?
The talk surveys, you don't have to wait till you've watched all the talks and then do it all in one fell swoop. You kind of use that talk survey, and this is the link for Livestream 4. We will put up a bunch of links later at the end to all 4 of the live streams. But you go in there, you pick your talk that you want to give feedback on, and it's super easy and super quick. And there's just 4 easy matrixed questions about that talk, and then you're done. And if you complete a survey while supplies last, you will get a cool pair of these Posette socks. So yeah,
I love that you have them ready to show off.
I have them ready to show off right here. I think they're beautiful. They're wild. They're crazy. If you're going to wear database socks, they need to be colorful. So yeah, please give people those suggestions. Tell them where you think they can do better, or just compliment them too. If there's something you really love. We also have sticker swag available to anybody who joins the virtual hallway track and pops on into the Discord. You could just ask for where to get the codes, where to get the link, and we will mail that to you anywhere in the world. So that is fun for people who love stickers. And if you're live posting, I mean, social media is so interesting these days. That's a nice euphemism. But use the PosetteConf hashtag so that we can see it, other people can discover it, we can amplify it. Yeah. And we should just pop in and look at the schedule for today's sessions. There are 11 talks, and rather than talk about them and dive in and read you the titles, we prepared a trailer, right? And it's gonna give you about 20 to 30 seconds from each of these speakers that'll tell you why that talk matters. So I think, what do you think?
Let's just roll that. Yeah.
Let's roll it.
Hi, my name is Derk van Veen. Today I will be talking about Postgres partitioning. This is my Postgres partitioning cookbook based on the past 4 years I've been building this experience with Postgres partitioning. If you are working with Postgres and you need to start with partitioning, this is a really good starting point.
Hello, I'm Ashutosh Bapat. SQL PGQ is the latest addition to SQL Standard. It allows relational data to be treated as if it is a graph. We have committed basic support for this standard in PostgreSQL 19. In this talk, you will get familiar with salient features of SQL PGQ standard and what has been committed recently.
Hi everyone, I'm Rahila Syed. I'm here to talk to you about a topic titled Journey of Developing a Performance Optimization Feature in Postgres. It is an exploration of how one can develop a feature which will improve performance of physical replication. This talk will be useful for developers who would like to contribute to Postgres or anyone who would like to learn more about physical replication.
Hi everyone, I'm Nitin Jadhav. I'm a senior software engineer at Microsoft and I work for the Azure database for PostgreSQL team. The talk you're going to watch is about PG DuckDB in action, accelerating analytics on Azure database for PostgreSQL. If you have ever wished your Postgres database could just answer an analytical query faster without you first exporting data somewhere else, then this talk is for you. By the end of this talk, you'll know exactly how PG DuckDB makes that possible, and you'll see it running live on Azure database for PostgreSQL Flexible Server.
Hi, I'm Chun from .NET Foundation. Have you ever deployed your Postgres database and other cloud services to the public cloud service? So sometimes you may have this question. Can I actually performance testing our infrastructure before we actually deploy it on the cloud? Well, today in my talk, I'm going to show you how we can use discrete event simulation to do the shift left performance testing on our infrastructure before we even deploy it on the cloud.
Hi everyone, my name is Kiran. Today we are going to track the full arc of logical decoding and replication. We'll go from its earliest building blocks in PostgreSQL 9.4 all the way to the multi-master distributed future that's being actively built right now.
Hi everyone, my name is Sakshi Nasha and I'm a software engineer at Cohesity. Today we're going to talk all about security in Postgres. Is your Postgres really secure or is it just working? Are you thinking of security as a design habit or just thinking it as an afterthought after you launch your product? So if you have security in mind and Postgres, this talk is for you.
Welcome everyone, my name is Shashikant. Today I'm going to talk about what I think is the most exciting area of improvement in PostgreSQL 18, vacuuming. If you ever dealt with the PostgreSQL database in production, whether that's on Azure, on-premise, or anywhere else, the changes which we're going to cover today directly affects how your database handles bloat, freezing, and overall maintenance.
Hi, I'm Mohammad Usama, and I'm going to talk about Citus cluster scaling. The recent version of Citus landed 2 new enhancements in this area, and I'm going to talk about both of these, how you can leverage those and what they are all about.
Hi there, my name is Jimmy Angelakos, and my talk is titled Listen Carefully, How Notify Can Trip Up Your Database. And it is a real world story. It's a thing that happened in production once upon a time, and it's a real pitfall and situation that can be caused when using this mechanism in Postgres. So I think it's really useful to talk about it and show you what it can cause and also how it can be fixed.
Hello everyone, my name is Hamid Akhtar, and today I'm going to talk about where does my insert go, a logical replication story. In this talk, we're going to start with an insert from the publisher to the subscriber database. So if you're planning on understanding the workflow of how logical replication works, this talk is for you. It will give you all the details about the wall, the logical replication, the decoding, and take you from the publisher to the subscriber.
Okay.
Great. Well, after that trailer, I just want to dive in, honestly.
Yeah, I think we should dive in. Although I really enjoy the snippets. So shout out to the team that produced the trailer and,
Absolutely.
all the speakers for giving us the super short bits about why this talk matters or who it matters for. All right, so let's keep going. Time to introduce our first speaker.
Yeah, and first up is Derk van Veen. I appreciate that you let me introduce him so I can, I can pronounce his name in Dutch, Derk is my fellow organizer at PGD Lowlands. But more than that, of course, he's a database specialist at Adyen. And Adyen has some very large Postgres databases under continuous high pressure. And an important part of Derk's job is to find creative solution for tough problems. And because sharing is caring, he often presents about the stuff that he learns at Postgres conferences or to the Postgres community. Like today, where Derk will talk about and will show you sort of the basics of partitioning and then some of the pitfalls and mistakes that he has made so that you don't have to make them yourself as well. So yeah, let's take it away, Derk.
Hi, my name is Derk van Veen. Today I will be talking about Postgres partitioning. This is my Postgres partitioning cookbook based on the past 4 years I've been building this experience with Postgres partitioning. If you are working with Postgres and you need to start with partitioning, this is a really good starting point. Right, let's open today's partitioning cookbook and see what I have for you. I've been working with Postgres partitioning now for 4 years. And when you work on something, you see it everywhere around you. I'm pretty sure you know this. And for me, this is the most cool example about partitioning, and I never expected to find it there. For me, the masters of partitioning are the supermarkets. They do partitioning everywhere, and it's so cool. Like if I enter my supermarket, first there is like the fruit and the groceries, or the fruit and the vegetables, but they are splitted. There's the fruits and there's the vegetables. And then next to it, it's like canned food. But within canned food, there's more partitioning. The things they want to sell first are at high level. And the things they don't mind selling are at different levels. And then even within a single tray, there is more partitioning going on. The cans, they need to sell first. The cans that expire first, they are in the front. And the things with a later expiration date, they are more to the back. And for me, that is such a good example of all the things you can do with partitioning. And it's just nice how a technical concept you can also find everywhere around you. And for me, that's something that makes partitioning really cool to think about. Like, how can I optimize all these things? I'm not running a supermarket, but I do have a lot of data. Try to imagine a supermarket where there's no structure. So you enter the supermarket and there's like chaos everywhere. And then you have like your index map and you look like X. Maybe track 6, 4th rack, and then somewhere on the top. And if not, go to the 6th or the 7th lane, and maybe it's somewhere there. It could be disaster, right? So how can we organize data with partitioning? That's the most important thing for us as database experts. So why would you start partitioning at all? Because let's be honest, it's a hassle. It is more work. It's probably going to hurt performance at least a little bit. And it's not going to make things easier. It's going to make things more complicated. Well, the most obvious reason to do it is the table size. Postgres has a physical limit of 32 terabytes. If you want to hit that limit and then think about partitioning, you are way too late. I would say if your tables are around 100 gigabytes, that's a good moment to start to think about partitioning. If your table grows to 100 gigabytes, not 100 terabytes, when your table grows to 100 gigabytes, your table's gonna grow probably also towards terabytes. And then it's already a little bit late to start to think about partitioning. So I would say 100 gigabytes is a good moment to start to think about, how do I want to partition my table? Or more importantly, how do I actually want to partition my entire environment? Because you can't partition a table by table. You have to partition all tables together. Because when your table gets too big, maintenance becomes really hard. And we don't like really hard tasks, right? We want life to be easy. And to keep maintenance under control, to keep vacuum timing under control, tables need to be nice and compacted and not too big, because then vacuum will take forever, and that's no good for anyone. And finally, data lifecycle management with partitioning is so much easier. Usually when developers think about cleanup, it's a cleanup job, and it runs once a month, then it starts to run once a week, and then it runs once a day. But every now and then this cleanup job fails, you need to debug it, you need to deploy it again, you become delayed, it becomes a hassle, right? But with partitioning, if data's old enough, you just take the partition, you drop the entire partition, and all the hassle is done. That's the way you want to do data lifecycle management with partitioning. So for me, these are the reasons to do partitioning. And there's only one good way to do partitioning in my perspective. And that is range-based partitioning. I know you can do hash-based partitioning and list-based partitioning. And especially developers usually love hash-based partitioning. I hate it. Because developers might say like, but yeah, then the insert logic, it spreads the load across all the partitions and it will be really fast. But at the end of the day, all the data needs to go to a disk, and that disk is not that good at completely random insert. And even more important, a hash is random. And if you have a lot of random inserts in your indexes, that's really bad for performance of your index. And you have to do a lot of maintenance work on the indexes. And if that's not enough for you, what if you have 10 hash partitions and you need more partitions? You need to go from 10 to 20. Suddenly, you need to redistribute all of your data, and you're doing partitioning, so you have a lot of data. That means you have to rewrite almost all of your data. That's a disaster. So, range-based partitioning is the only good way to go, at least in my opinion. So instead of one big table, we have just chunks which are smaller. And the most natural one, I would say, is date-ranged partitioning. So in this example, I could just store data for the first 3 months of this year. And if I'm collecting PII data, I see like, oh, this data has been collected in January 2026. So in 5 years' time, I can easily drop this partition and all my PII data will be gone. That's how easy partitioning can make this task for you. But we are working with a relational database, so we have a lot of relational data. That means probably you use a integer type as your primary key. I would say that's a high probability. And then probably you want to partition on this integer type because the partitioning key has to be part of your primary key. Otherwise, we can't enforce the uniqueness over all partitions. And there's one more thing. You can have a default partition. And I have mixed feelings with default partitions. The default partition is kind of a catch-all, which is really convenient because it means by definition you cannot run out of partitions. If I try to insert value 5000 in this partition table, it ends up in the default partition. No harm done, application keeps running. But then what do you do with this default partition? Because suddenly I can't create a partition anymore from 5000 to 6000 because that means moving data around from a default partition to other partitions. So it's also a little bit of a trickery. And in Postgres 18, if you look at the partitioning constraint for a default partition, it will say default, and that's it. But if you have older Postgres versions, I don't know when the switch happened, but the default constraint used to be listed as not all of the other ranges. And that's really problematic. So the default partition, it can be a lifesaver, it can be a blessing, but it's also definitely a curse. Because locking with the default partition is really hard. If I need to add a partition, I need to change my partitioning constraint on the default partition. That means I need an access exclusive lock on my default partition. That also means I need to wait for all my transactions on the cluster, hence the cluster, not the database, to finish to get that lock. So that can be a really long waiting time for a very simple operation, and that's why I don't like it. But this is where the default partition has been a lifesaver for me. I had multiple tables in completely different ranges, and they were all feeding into one bigger table. That bigger table, that was the one growing, so that one needed partitioning. But how can I partition this big table? If I partition this one from 0 to 1010, I cannot have partitions in between. So how do we solve this? Well, I created this big table. I made it my default partition. That means I can have a constraint that is not all of the other constraints, right? And on top of that, I added a check constraint saying like all data in this default partition will be between 0 and 10, between 100 and 110, and between 1000 and 1010. And that means I can now create new partitions next to this partition. And these smaller partitions, they will catch the new values coming in. So I can store my values between 10 and 20 here, and between 110 and 120, etc. So this is where the default partition saved my life, or at least it made my life a lot easier. But yeah, you have to be really, really careful with its usage. And this is my favorite part of partitioning. And this is also where most people get nervous, because when I'm working with partitions, I cheat a lot with the catalog. And I agree with you. Cheating with the catalog is a bad plan. But if it's the only option you have, why would you not do it? Just be aware that you need to be careful, right? So I have a partition table here with just a few partitions. Now, sometimes I need to do work on one of the partitions. Maybe there's a cleanup I need to do. Maybe there are corruptions. Maybe, I don't know. Over the years, there have been plenty of moments where I needed to detach a partition, do some work on it, and then attach it back. So what I do, I detach it. Detaching is easy. Detaching can be done concurrently since Postgres version 14 from the top of my head, but only if you are not having a default partition. Remember how hard it is to change the constraint on the default partition. But now, if I want to add a partition back, the Postgres will enforce that all the values within this partition are not violating the partition boundaries. That means while I add this partition will be logs by Postgres, and all the values will be checked if it's not violating the partitioning constraints. So I don't want to have this long-lasting log. So what do? I create a check constraint saying like all values in this partition are exactly matching the partition boundaries, or at least not violating the partition boundaries. And I add this check as not valid. Why do I add it as not valid? Well, that means I have no locking time. And if I want to validate my data in this table, I can do that. But I can also just update my catalog. And this is where the cheating comes in. And this is dangerous because I can put any value in this table and then attach it as a partition. But it's also a way to attach a table with data in just the time it takes to do a catalog operation. Because adding a table as a partition, strictly speaking, is just a catalog operation. It's just be careful. I created multiple incidents with this technique. Maybe my developers did it on my behalf, but I created the sources for them to do it. So be careful with it, especially at the boundaries. The lower boundary is included in the partition, the upper boundary is excluded, and that is where the mistakes came in my case. I actually included a row with ID 2000 in the second partition, while it should have been in the third partition. And when you ask for the data, you cannot find it unless you do a select all from a given partition. Be careful, but still, this is the best way I can think of to do these kind of operations really fast and without any locking. And then also this one, a lesson I learned over the years multiple times. But every operation you do with a partition table, adding indexes, foreign keys, detaching a partition, attaching it back, it all changes the structure of the partitioned table. And let me give you an example. I just have a partition table T1, stupid name, I know. If I want to add indexes to this table, if I would add the index on the parent immediately, I cannot add the index concurrently. It's not allowed on partition tables. But what I can do is create the indexes concurrently. And I start at the oldest partition and then I work my way up all the way to the top. And only when all the indexes are in place on the partitions, I add the index as well to the parent. So I enforce all the new children also to have this index. But that's also a problem, because if I want to drop this index now, I have no way of dropping this index easily. I cannot drop concurrently from the children, and I can also not drop concurrently from the parent, because it's a parent table, it's not allowed. So dropping indexes from a partition table can be really hard. So be aware what you are doing. And this is another example where I was really surprised. I have two tables here, two partition tables, and I have a foreign key between these two tables. And then again, I needed to do some cleanup on one of the partitions, and I did my trick. So I detached the partition from its parents, then I was copying rows out, doing stuff in, all good. And then I attached this table back to the parent. But what happened? Suddenly, I have a lot more foreign key references between these tables. First, I only had a reference between the parents, and now suddenly I also have references between children individually, because I created a foreign key on a table which was not part of the partition table, so I changed the structure. Be aware of all these kind of unexpected behaviors with indexes, foreign keys, constraints. Just be aware. And yeah, probably no need to tell you this, but manage your partitions automatically in one way or the other. You don't want to do this manually. You will be successful, the developers love it, and suddenly all you do the entire day is managing partitions manually. Don't go there. All right, next part, joining tables. It's the hardest part of partitioning, I would say, because there are so many ways to go wrong with partitioning and joining partition tables with each other. So let's say I have two tables, a payment table and a ledger table. And we are doing a lot of payments within Adyen. Adyen started as a payment service provider. So we have a lot of payments and we have a lot of ledgers. So if you join a lot of partitions with a lot of partitions, that's a lot of work. If you want to save work, I always tell people the fastest way to do something is don't do it at all. The fastest way to read from a partition table is to only read from the partitions you really, really need. So in this case, I'm joining payment and ledger, and I'm searching for a specific ID. So this ID can only live in one partition for the payment table and one partition for the ledger table. So this is what I want. Well, good, right? Nothing wrong. But now if I make my where clause slightly more complicated, I expect it to read from 2 payment partitions and from 2 ledger partitions. But instead I'm reading from all the ledger partitions. And in this example on my slide, it's only 3, but in reality, this might be 50 partitions. I don't want to read 50 partitions. I want to read 2 partitions. So how do we fix this? Because this is a really big problem. Because if I don't fix this problem, my query gets more expensive with every partition I add. That's not what you want. So what is the solution here? You have to align your partitions around your leading figure. So you have to pick your leading figure. Pick one from history you like the most. No, that's not going to work. Okay. So we are doing transactions, financial transactions within Adyen, right? So for us, the leading figure would be a financial transaction, in this case. And that ties together the payment, the ledger line, and all other kind of things related to transactions. So for me, for my system, the leading figure would be the transaction. For your system, it's probably a different column. But if you have a lot of tables with the same primary key, most likely that is your leading figure. And then the trick is to align all your tables. I will say it again. You have to align all your tables around this leading figure. And I will show you why. So here's the payment ledger example again. We know this is very inefficient. But let's see what happens if I align my partitions. So what do? I have to make my ledger partition slightly bigger and then pick exactly the same upper and lower boundary for all of my children. So now it looks already visually more appealing, right? And this also counts for Postgres, because if I now have data in one partition, I immediately know then the data I'm joining is exactly on the other partition. And that counts for the first one, the second one, the third one. And this is where the efficiency comes in. So let's see what happens. If I now do exactly the same query, it still doesn't work. We are getting nowhere. Well, hang on with me for just one more minute. I will show you, because there's one more trick we need to do. We have to set enable partition-wise join to on, because it will make the planning of joining with partition tables a little bit more expensive. But you pay a little bit of planning time, but execution time, you're scanning 2 partitions instead of 50 partitions. And that is going to save a lot of logs. You will save a ton of time on your log manager, and you're saving a lot of time on scanning partitions you don't need. So this is the real lifesaver. And with this setting on, and I run my query, finally, this is where I only reach from the partitions I really, really need. And this is how you gain maximum performance with partition tables. This is the trick. But I know how this goes. Sometimes you have an associative table between 2 tables. So in this case, between transaction and ledger, I have a transaction ledger table. How do I fix this? Because if I want to join a transaction with a ledger, they are not even partitioned on the same column. So this query will be expensive by definition. There's nothing I can do. So how can we solve this problem? And this is not an easy one. I totally agree with you. But all we can do, and all you can do, is this. You have to denormalize the ledger table. There's no other way around it. You have to include your leading figure with the ledger. So in my case, the transaction has to be included in the ledger table. That means I need to change my query. I need to check my query logic. And this is a lot of work and a lot of hard work. It's complicated, but the difference in performance, it's huge. So if you really want to maximize performance, this is the step you need to take. So finally, a little bit about archiving your data, because that's the final cool thing about partitioning. That's what I told you at the beginning, right? So very briefly go through. I always have a table with at least 3 available empty partitions. Why? I hate to run out of partitions when I'm trying to insert something. And over time, partitions will fill up and I will create new empty partitions. And then after a while, my table will look like this. I have a lot of filled partitions and still I have a lot of 3 empty partitions to go for the future. Let's say this is the set of data I really care about. That also means now I have 1 partition I don't need anymore. So what to do with this 1 partition? Well, if this is just logging data and this is more than 10 days ago, I can just detach this partition and throw it away. No harm done. But sometimes I don't want to throw data away, but still I don't want to keep it in my primary system because it will slow me down. So what to do with this single row? Well, if I can't throw it away, but I don't want to keep it in this system either, I have to find another solution. I have to archive this data. So I can just have a big archiving database. I copy my data there. And if I really want to make this transparent to the application, I can even have a foreign data wrapper pointing to this archived data. But I will discourage you from doing this. It's a lot of work to maintain this. It's easy for me to draw an arrow from, hey, I have a primary system here and an archive here. Just have a foreign data wrapper. But in reality, this is a lot of work. It's complicated and a lot of ways to keep track of. So I would tell your application developer, this is your job to keep track of. But it is possible within Postgres to do this. So, summary. In my opinion, there's only one correct way of partitioning, and that is range-based partitioning. Hash-based partitioning, I strongly discourage you of using it. It is dangerous with respect to performance, and it's really dangerous when it comes to scaling. I know there are really cool solutions around where hash partitioning is the solution, but then you have to be extremely aware of what you are doing. And if you're just starting with partitioning, I think that's not where you are and not where you want to be. So please hear me out. Start with range-based partitioning. It's really much easier to handle. And then find the leading figure in your data. The leading figure is the one data unit bringing all the tables together, and that's what you really need for efficient joining. If you are not partitioning your tables all together in your environment, performance is gonna degrade over time dramatically, and that's gonna be really painful to fix. And finally, partitioning is also really good about data lifecycle management. Just detaching a partition and dropping the table, it's so much easier than a cleanup job. So if you know you're storing PII data, partition it by a date, get rid of it. Even if you store this by a integer type primary key, have a way to calculate how old the newest data in a partition is, and after that moment, you can throw your data away. It's really, really easy. If you want to have a quick start about partitioning, we have a partitioning framework. It needs some love, but still, I think this is an amazing start to build your own partitioning framework. I will try to update my partitioning framework again, but no promises there. I'm kind of busy. If you want to read a lot about partitioning, I published together with my colleagues 5 blogs on the topic, and maybe a 6th one, but it has a slightly different name. But that is a really good starting point where all my learnings about partitioning are listed. So I hope this is a really good starting point for you to learn about partitioning. It's a lot of background knowledge if you want to have a full read on the topic. And now I wish you all the luck with your partitioning journey. Have fun.
Have fun. That's pretty good. I really love the chat in Discord, Claire, where there's conversations going on about, patches to maybe solve some of the challenges that Derk is mentioning. That's what, such a hallway track is for. So I'm glad to see it.
I think he does mean it when he says have fun too, because every time I've talked to Derek about his job and what he does at Adyen, he seems to really enjoy it. So he is having fun with it. And partitioning is definitely something he has spent a ton of time on. I don't know if he's hit that 10,000 hours expertise mark yet, but I wouldn't be surprised as a practitioner. He probably has.
Yeah.
So
super good.
I know he works on his public speaking skills too. Like, and he even gives talks about giving talks, which I think is helpful. All right. I think we should move on, right? You ready?
Sure thing. But yeah, definitely. I mean, because Derek is investing in public speaking for himself and for the rest of the community, he will appreciate feedback more than most people. And also because he's Dutch, of course, you can be very straightforward with your feedback. You don't need to sugarcoat it, or how did they say that? Like a shit sandwich, where you're complimenting, then you give feedback, and then you're complimenting again. You don't need to do any of that with Derek. So
just go straight to the suggestions.
Give it to him straight.
For anybody who arrived late, the deal with the talk surveys is you don't need to wait till you've seen all the talks that you're going to want to submit on. And actually, the deadline for the talk and the event surveys is next Monday at 11:59 p.m. anywhere on Earth time zone, which means anywhere on Earth. So you can submit one talk at a time. And it's super easy. You just pick that talk. This is the LS4, the Livestream 4. Survey QR code. So for what you're watching here today, but yeah, we've tried to make it super easy. And then while supplies last, there are socks available as our way of saying thank you for doing this. And then the event survey, that's for the whole thing, the website, the CFP, the live streams, everything about the conference. Okay. Also, if you're just joining, reminder, there is a Discord, there is a hallway track. It's not the same as in person, but it can be quite fun. So
yeah, for sure.
Speakers are there for all the talks while their talk is being live streamed. So you can ask questions, which can be super useful, right?
Absolutely. And speakers are commenting on each other's talks too. So it's interesting to watch and read.
Even if you haven't filled out a survey yet, if you want stickers, you can go ahead and find out how to do that. There should be a swag thread in the Discord as well. So if you head over to the Microsoft Open Source Discord, you can just enter your information we'll ship these anywhere in the world. And I think it's time to introduce the next speaker. So Ashutosh Bapat is the major contributor to the Postgres open source project. Major contributor is a term of art, if you will, in the Postgres community. These are people who have been recognized for many years of contribution and service to the project. He works at Microsoft on the Postgres open source team here, and he's based in Pune in India. He is thoughtful, he is dedicated, he is hardworking, and he's done a lot of work in Postgres in the areas of partitioning and foreign data wrappers and logical replication and something called SQL PGQ. And so this talk is about exploring property graphs with SQL PGQ in Postgres. And one of the things that I think is super fun is he uses a board game for the game Ticket to Ride to walk through and help people understand this new capability that's now, right now, Postgres 19 is in beta, and support for SQL PGQ was added to Postgres 19, and GA isn't out yet, but it's there right now. So that's kind of exciting.
Super interesting. Yeah.
So let's dive in and roll this video.
Hello, I'm Ashutosh Bapat. SQL PGQ is the latest addition to SQL Standard. It allows relational data to be treated as if it is a graph. We have committed basic support for this standard in PostgreSQL 19. In this talk, you will get familiar with salient features of SQL PGQ standard and what has been committed recently. Let's start exploring property graphs with SQL PGQ in PostgreSQL. Let's take Ticket to Ride, the popular board game, as an example. What is SQL PGQ? It's a SQL standard, part 16, added in 2023. It introduces a concept called property graph. It is the same graph with nodes and the edges connecting those nodes. But these nodes and edges have properties associated with them. And these nodes and edges can be classified into different classes. This standard allows relational data to be treated as a property graph. It overlays a logical view on the relational data. It consists of declarative graph query language so that this graph can be queried in terms of nodes and edges and not in terms of joins and unions of rows. There are other RDBMS implementations available. And good news is we have committed basic SQL PGQ support in PostgreSQL 19, which will be released later this year. Let me introduce Ticket to Ride, a board game which I'm going to use as example. In this game, the board contains cities and routes connecting these cities. Or I will say it contains places like cities, countries, and the routes connecting these places. Each player is given few tickets, and each contains a pair of these places. A player gets the points for that ticket when the paths, when there is a path connecting the places on that ticket claimed by that team. It's a turn-based strategy game. And as you will see that it is a graph in computer science terminology with cities or places as nodes and the routes as edges. For this talk, I'm going to use a simplified hypothetical graph as shown with the cities in blue bubbles and countries in pink rectangles connected by routes of varying length and with different points. Now let's suppose we want to use PostgreSQL to figure out how to play this game, the strategy for this game. What we need to do is first we have to convert the data on the map into relational data. So let's start creating tables. The first table is cities. It has primary key city ID, name as other column, and there is one row for every city on the map. Second, similar table countries, country ID as primary key, name as another column, and one row for every country on the map. Let's also add two more tables for the routes. One for the routes connecting cities with route ID as primary key and city ID as foreign key referencing cities. Length, color, points claimed by are columns corresponding to the properties of these routes. And there is one row for every route on the map. Similarly, for country to city routes, again the same set of columns, except that country ID and city ID are foreign keys into respective tables. And one row for every route between country and city. We started from the data on the map, which was graph, converted into relational data. But in order to think in terms of graph and find paths which are optimal, we need our graph view back. And that's where the first feature of SQL PGQ helps. It allows to create a property graph. In this case, let's name that graph as TTR graph. There are two major components to this property graph, vertex tables and edge tables. Vertex tables are the tables which contains nodes, and the edge tables are tables which contain edges. You must have figured out by now that there are two tables which contain nodes, cities and countries. Their keys are the columns in the respective tables which identify the nodes. Next come label, which give the class of that node. So all the rows in cities table belong to class city. All the rows in countries table belong to class country. And each of them has only one property named name associated with them, which corresponds to the respective column in the respective tables. That's about the vertex tables. The next is edge tables. Edge tables have the same components as the vertex tables, but they have two more components which define the source and the destination nodes of a given edge. So, and the corresponding keywords are source and destination. You will see that in the first edge table, city routes, we have source key references clause. It is nothing but the foreign key in the city routes table referencing the cities table. When that foreign key is clear, as is in example of country city routes, we can get rid of the key references part of that component and just say source is countries, destination is cities, so that it knows that the edges of country city routes have their starting vertex in countries table and the end vertex in cities table. Similar to vertex table, edge tables also have labels and properties associated with them. In this case, we are using the same named label root for both the tables. So in SQL PGQ, a given vertex or edge table may have multiple labels associated with it, or a single label may be shared across multiple vertex or edge tables. In fact, we can share one label across vertex and edge tables as well. The only condition is each label has to have the same set of properties associated with it. For example, in this case, root ID, length, color, points claimed by exactly the columns of the respective tables are mapped to the properties of label root. These properties need not be one-to-one mapped to the columns. They can be expressions containing the columns, or they can be expressions which may not have even the column names. All that flexibility is allowed in the standard. So we started with map, the data in the map. We converted it into relational data, added property graph on top of it, and now we can visualize that relational data as if it's a graph. The same, it goes to the map. In the next slides, what I'm going to do is I'm going to introduce features of SQL PGQ one by one. Not all of them are implemented in PostgreSQL. The ones which are implemented are highlighted in green color. Those for which there is some patch proposed, those are blue, highlighted as blue. The ones which are under design, they are in brown. And for the features for which we haven't even started thinking, they are in red. Okay, let's start with our first exploration. Let's start with simple one-stop route. What we want to do is we want to find all the paths between two cities, Mumbai and London, which have exactly one city in between. So we specify in order to specify a graph, a property graph in the SQL query, we use graph table construct enclosed in parentheses. To that, we specify the property graph name. After that comes the match clause. In the match clause, we give the pattern which we want to explore for a substructure in the graph. Typically, a pattern is sequence of vertex patterns and edge patterns. A vertex pattern tells which vertices can be placed at that position in the path. Edge pattern tells which edges can be placed at those positions, at the corresponding positions in the path. For example, here we have 3 vertex patterns and there are 2 in between edge patterns. The 3 vertex patterns are named A, Con, and B. All of them have optional 3 components. One, the name. Second, the label, which in this case for all of them is city, because we want to find paths which have vertexes of class city. And last is the filter condition. In this case, where a.name equal to Mumbai for the first vertex pattern and b.name equal to London for the last vertex pattern. So that specifies that the first vertex has to be one with name Mumbai and the last vertex in the path has to be one with name London. The stop can be any city. It cannot be country. That we specified by giving the class in the form of label. Edge pattern is similar, except that the vertex patterns are enclosed in parentheses and edge patterns are enclosed in brackets with dashes around them. These dashes sometimes have arrows indicating the direction, but in this case, they are directionless. So for both the edge patterns named R1 and R2, we are going to be using the same label. So those roots or the edges can come from either table. Given that we are constraining all the vertices as cities, only the roots between the cities will be chosen. The last part of this graph table construct is columns. So we told what substructure in the graph we want to explore. But columns tells what properties of that substructure we want to project, we want to use in the query we are looking for. So in this case, we are looking for the name of the first city, the last city, the connecting city, and the total length and total points of these paths. Before moving ahead, I will digress a bit and explain what happens to this graph query. So it undergoes a transformation which has 3 stages in it. One, we convert element patterns into element tables. Second, we convert path pattern into union of joins. And third, we replace all the property references into the corresponding column references. So when we are converting element patterns to element tables, we take the label expression, compute set of labels from it, and for every set of labels, we compute the properties associated with it, as well as the vertex and edge tables that belong to that class of labels, or the class that is determined by the set of labels. A path pattern is broken into sequence of element patterns, and for every element pattern, we calculate the set of vertex and edge tables. If you visualize this as some sets, like it becomes a k-partitioned graph with k as number of vertex or edge tables. Executing this query or transform this query itself becomes a depth first search through this key partitioned graph. So each path then gets converted into sequence of joins that the path is a result of this depth first search. And then the set of paths, which are all the permutations of these k sets of elements, those are combined using unions. At the end, we convert property references into table column references. After this transformation, what we get is a pure SQL query. So we take graph query, convert it into pure SQL query, which is executed as any other regular SQL query through the execution engine. So on the left side, you will see the graph query that we started with. On the right side, you will see the corresponding equivalent SQL that was generated out of these transformations. And here is pictorial example of the roots that we got as a result. We are just highlighting 2 roots here. Next feature I want to discuss is label disjunction. In the earlier query, we were interested only in the paths that go through city, but let's say we are also interested in paths that go through countries. All we have to do is say that change the label expression to city or country, and that's it. The edges are already using label root, which covers all the routes between cities as well as countries, so we don't have to change anything there. And here is the resultant SQL. All we did was a slight change in the label expression, and that resulted in double the size of the SQL query. Now there is the union leg added corresponding to the countries. And this is true with every small addition to the graph query, which results into an exponential growth of the SQL. That is the strength or power of the SQL PGQ, that it is expressive and expressed in terms of graphs rather than writing this humongous SQL. Again, example paths that we found, and you will see one more path which goes through South Africa. In real ticket to ride, we won't be constraining ourselves with just 2 route edges. We want them to be as long as possible, covering all the tickets that we want. So here we introduce concept of variable length paths. You will see that the edge pattern has a little annotation to it, 1 to 5. It tells that I want all the paths between Mumbai and London of length at most 5 edges, with at most 5 edges in it. Now remember, all the features that we talked were highlighted in green color in the earlier slides. They are part of the implementation. This is brown, so it's still under design, but the thinking has started. These variable length paths can contain cycles, which of course we want to avoid when we are playing this game. So we specify a match mode, acyclic, to eliminate paths with cycles in them. It is red, highlighted in red, so not implemented, not even started. Next, I'm introducing a very powerful feature of SQL PGQ. It allows aggregation across variable length paths. For example, here we want all the routes that are part of the path, as well as the total lengths and total points that those paths will give us. These aggregates can be anything. In this case, it is sum, but you can use average also, or any aggregate of your choice. SQL purely does not allow aggregation across joins, but SQL PGQ, through this feature, allows aggregation of joins taking the aggregates to the next level. See the corresponding SQL, again becoming more and more complex. I want to highlight here that this SQL was written with recursive query, but it could be also written using joins and unions, 2, 3-way, 5-way, 7-way joins. So somebody who wants to write SQL corresponding to graph query now has to leave the declarative nature of it aside and start thinking in terms of implementing it in SQL. SQL PGQ gets that declarative nature of SQL back, because now you can, with SQL PGQ, you can just declare what you want from the graph and not necessarily how you want to implement it in the SQL. That's the part of rewriter. Example roots, one root of 3 length and the other with 4 roots in it. 2 paths, one with 3 roots and other with 4 roots in it. Next, I'm going to introduce feature for which I chose ticket to ride as an example. In ticket to ride, you are given multiple tickets with pair of cities. So what you want is to you explore or find out the substructure within the map which connects all these tickets. And so multiple path patterns features allows that to be done in SQL PGQ. In the example query, we are specifying 2 path patterns. One, variable length paths between Mumbai and London, as well as variable length path between Paris and Tokyo in the same query. Don't forget acyclic, because we don't want either of those paths to contain cycles. Remember, this is blue, highlighted as blue. So there is a patch actually proposed on Hackers for this feature. I won't even bother reading the equivalent SQL. It's too clumsy to even start thinking about it. Here are example routes again. One between Paris and Tokyo, other between Mumbai and London going through Germany. As we approach the end of this presentation, I'm going to give you a quiz. Using a previously seen query, which I have repeated on this slide, I want you to write a query which will find whether team A has claimed all the paths connecting Mumbai and London. Supposing Mumbai-London is their ticket, whether team A is going to get the corresponding points or not. You have to make a small change to this query so that it answers our question. I will come back with the answer after a few slides. I want to highlight that what SQL PGQ is not. It's not a native graph database. It does not specify how the storage should be. The relational data remains relational. We do not have optimized storage specified according to SQL PGQ. All SQL PGQ gives is this declarative, powerful language through which we can explore substructures in the graph or graph patterns within the graph. Those who have been using PostgreSQL for their graph applications must be familiar with Apache Edge, which is an extension providing graph query facility on top of PostgreSQL. A natural question is, what happens to Apache Edge once SQL PGQ lands in the core? I think they have a very good symbiotic future. SQL PGQ will continue to focus on SQL PGQ features, optimizing those, whereas Apache Edge will continue to focus on portability, migrations. It will continue to provide the Cypher query language layer on top of PostgreSQL. It can use SQL PGQ to optimize it further. I see this relationship evolving in a similar fashion as the relationship between partitioning, which is a core feature, and PG Partman, which is an extension evolving, has evolved over the years. Of course, you may want to choose SQL PGQ when you are writing new applications. Okay, let's come back to the quiz. And the answer is, all you have to do is add a where clause in the age pattern, which is r.claimed by equal to team A. It is highlighted in green, so it is supported. Is a supported feature. With that, let me end my presentation. Thank you for watching this presentation, and we will take questions in the Discord channel. Thank you.
That was an awesome talk by Ashutosh Bapat.
Yeah, super well done. I loved, like using a game to explain concepts and a quiz at the end to keep everyone engaged. So really well done. So I know that my colleague at EDB and one of the core members, Peter Eisentraut, said that he is not able to follow along with Posette today because he's at a SQL standards meeting. But that he really wanted to organize a watch party to watch this particular talk from Ashutosh with a couple of other people. And then when he said watch party, I realized, Posette is basically one big watch party. And so yesterday we even had at my house, we had the live stream on the big screen, the big TV screen while we were working. And it's such a nice way to, follow such an event. So yeah, really cool and fun.
Oh, that's awesome.
Yeah.
And I know that obviously all the talks are getting published online as individual talks with all those high quality captions like we mentioned. But I also know, because people have told me, that some people will watch this live stream, which is available on YouTube later to be replayed, because apparently they get a kick out of the banter in between, and they like seeing the talks like in the order that they were designed. Whether it's with popcorn or snacks or I don't know. Obviously 6 hours is a lot, but you kind of pick the 3 or 4 and anyway, kind of neat.
Yeah.
Let's keep going. There's the link to the talk survey and the event survey for those of you who are just joining. Super easy to do, super valuable for people, and you'll be able to, if you submit it per the deadline, get access to one of those cool, bright, colorful Posette socks. And now it's time.
Yeah, for our next speaker. So Rahila is a Postgres developer and used to work for Microsoft and EDB. Unfortunately, we just missed each other at EDB, but has been working as a Postgres developer for 13 plus years. It's also not her first Posette rodeo because last year she talked about designing a monitoring feature in Postgres. And today she'll talk about sort of the journey of identifying and optimizing a performance bottleneck in Postgres.
Hi, Rahila.
So let's dive right in.
Hi everyone, I'm Rahila Syed. I'm here to talk to you about a topic titled Journey of Developing a Performance Optimization Feature in Postgres. It is an exploration of how one can develop a feature which will improve performance of physical replication. This talk will be useful for developers who would like to contribute to Postgres or anyone who would like to learn more about physical replication. So let's get started with a journey of developing performance optimization feature. Let us look at the basics first. What is physical replication? Physical replication is a block by block or byte by byte transfer of vault files from master server to the standby or replica. It transfers the entire database from one master to the replica. It does not transfer just selected tables or columns or rows of a few tables. It transfers the entire database. What are the different types of replication? Synchronous and asynchronous replication. This replication type is set using GUC parameter, which is named synchronous commit. There are various settings to this GUC parameter. One is off, which means it is asynchronous replication. The commit of a transaction on master does not depend on whether the change is sent to the standby or the wall records corresponding to the change is sent to the standby or not. Master commits its transaction and gives confirmation to the user without waiting for the transaction to be locally flushed to disk as well. So there can be a delay between sending a response to the user that the transaction has been committed and when the transaction actually is made durable. This can be done for performance reasons. The second setting of this GUC parameter, which is synchronous commit, is local. This setting means that the transaction is considered as committed and a user is notified of its commit only when the transaction has been flushed to disk. This is the mode which guarantees the durability of a transaction. The third mode is remote write, which means that a transaction is considered as committed on primary only if the transaction has been written to a file on standby, which is the wall file. This does not mean that it has been flushed to disk as well. It just means that it has been written. The other mode, fourth mode, is remote flush, which you might guess that the transaction is considered to be committed on primary only when the transaction has been flushed to disk on standby. Remote apply means that the transaction on primary is committed only after the transaction or the wall corresponding to the transaction has been written to the files, flushed to disk, and also the changes have been applied to the database on standby. So whatever you read on primary can be read instantly on standby. Let us move on to look at the flow of wall files in physical replication. There is a primary server where your data changes are made, like inserts, updates, or deletes. These changes are logged in the form of wall records. This results in wall to get inserted to first wall buffers, then they are written to disk, and finally they are sent they are flushed to disk, and then they are sent to the standby. At standby, there is a wall receiver process which directly writes these wall records that are coming in from primary to wall files. It does not have any buffering there. After writing to wall files, these wall files are then flushed to disk. After getting flushed to disk, there is a starter process on the standby which reads these wall records from the wall files and applies them to the database. So as you can see, from the time the data is written on the primary to the time the data is available on the standby, there is a bunch of round trips to disk that happens both on primary as well as standby. Now let's look at what wall buffers are. As mentioned before, the changes made to the database are written or logged to the wall files. First, these wall records are written to wall buffers, and then they make their way to the wall files. So these wall buffers can be set by a GUC parameter. These are typically about 3% of shared buffers. Setting this value high is important if you have lot of concurrent workload, lot of backends connected to Postgres, writing and reading to tables. because all of these backends that are started on your Postgres database write to the same wall buffers. However, setting this value too high is also not recommended because this will definitely hamper the memory consumption of your computer. Also, the wall files or the wall buffers are flushed periodically by wall writer process. So for very small transactions, we make sure that the wall buffers are consistently flushed to disk, so the wall buffers can be reused by other backends. So this should not be set to very high value as well. Now let us look at wall fsync. Fsync is something when we flush the wall records to disk and they are made permanent and durable. For a synchronous commit, it happens during a commit on a primary by calling xlog flush. There is a process called a background writer, wall writer, which does the writing or the flushing of the wall records in the background. It tries to not hamper the progress of the transaction that's running on your database. It periodically tries to flush wall as and when wall buffer starts to grow. It tries to keep it in check because if it becomes full, it will start slowing down the active transactions because they will not have space in the wall buffers to write their own changes. Wall writer works on writing wall records to files and periodically it also flushes them. Flush of wall files by wall writer depends on certain juicy parameters like wall writer delay and wall writer flush after. If the last flush happened less than wall writer delay ago and less than wall writer flush after worth of data was produced, the data is only written to OS buffers and not physically flushed to disk. So now let's look at how to identify bottleneck in the wall sender process. This is the wall sender main loop. And let us see what are the operations that are happening in the wall sender main loop. Wall sender is a background process in Postgres, which is used for sending wall records from primary to standby. It runs an infinite loop, and these are the operations that happen in that loop. As it starts, there are some housekeeping tasks that are happening. First, what you can see is a reset latch. Latches is used by wall sender to wait for the network socket to get ready. It sleeps on the latch till the network socket is ready or till new wall records are available in the wall buffers to send. Then there are other checks for interrupts because it's a long running process. It needs to be interruptible. There is another task where the configuration parameters are reloaded in the process, so that what's happened in a wall send handle config reload, followed by processing replies from the standby. Moving on, we can see a decision box, and that is the exit condition. The exit condition check in that loop checks if the standby is done receiving wall, which is indicated by copy done, as you can see on the screen, or if the output buffer is full. So when both the output buffer and the copy done are true, output buffer being full and copy done are true, the wall sender will exit. This is the regular or a clean shutdown of wall sender. Output buffer is something that is used by wall sender to copy wall records from wall buffers to the output buffer before sending the output buffer over the network. So if the exit condition is not met, which means either the output buffer is not empty, there are still wall records to be sent, and copy done also has not been received, then it will go on to check if the output buffer is empty or not. If not, then it goes on to flush that output buffer to disk. Sorry, flush that output buffer to network. If the output buffer is empty, it will go on to read the wall into the output buffer. So this happens from either the wall buffers or the wall files. First, wall sender checks if the wall is present in buffers and reads from the wall buffers, otherwise it reads from the wall files. In case of large transactions, it happens that the wall sender has to go to disk because the transaction takes a long time to commit, and by the time the wall sender is ready to send this transaction, the wall buffer eviction logic has kicked in, so the wall records are no longer present in the wall buffer and the wall sender has to go to disk. This logic happens inside the read wall into output buffer block shown on the screen. So when the output buffer has been read, it is ready to be sent to the network as shown in the slide. If output buffer is not empty, it goes on to try to flush that output buffer over the network, like you see. So once that completes, it goes on to see if the wall sender has caught up or if the output buffer is full. That means there is a lot of wall in the output buffer to be sent to the network. So that is when the wall sender sleeps, because there is a lot of work to be done on the network front and wall has to be sent over the network. So there is no point burning CPU cycles of the wall sender. So it sleeps till the output buffer is available to be written again, or it also sleeps until there is new wall record present in the wall buffers to be sent across the network. Now let us look at particular wall sender behaviors. One of them is that the wall sender currently sends wall records only up to the last known wall record that has been flushed to disk. This is done for a simple reason that we cannot have standbys get ahead of masters, because at the standbys we don't buffer anything. We just completely go ahead and write to wall files. So we need some gate check where we guard the wall files being sent to the standby, because we don't want to be written and made durable on standbys before they are flushed to disk on master. Also, for large transactions and which are long running, it happens that they accumulate in the wall because commit has not happened yet, and the flush of the transaction has also not happened, which results in them accumulating in the wall buffers. So going on inserting the wall records and generating more and more wall cannot send them over the network because the flush has not happened, and this results in the network being underutilized. When the transaction commits, you'll send all of these records in burst across the network. So that time the network will also get overwhelmed. This can also result in increase in the disk I/O, because since a large transaction can occupy space in buffers for a long time, chances of it being written out are higher, and thus it means that when wall sender is ready to send it, it will have to go to disk to read it. So let us look at perf profiling. This is used to profile the CPU consumption of a particular process. It samples the execution of various instructions on the CPU at a fixed interval, so that when it is aggregated, you know where most of the CPU time is spent by the particular process. It also contains a call graph structure which records the full stack traces. So the commands that I've used for profiling are shown on the screen. Perf record generates perf.data, which is then used by a tool called Flame Graph, which is used to visualize these call stacks and make it easier to understand. So let us look at the benchmark that I've run to profile the wall sender and the wall receiver. The slide shows the details of the benchmark. And the configure flags used to compile Postgres is shown on the screen. We use O2 for compiler optimization, which results in improvement of the performance of Postgres cluster. Also, PG bench is used, which is a TPC-B-like benchmark. Essentially, what I've tried in this benchmark is to have enough concurrent clients so that the wall buffers are used to their fullest, and the wall sender has to go on disk more frequently to be able to send wall records. So I have used somewhere from 16 to 32 concurrent clients. -J is the number of worker threads, which is set to match the CPU cores. -F is the custom workload. This is what happens when the PGBench benchmark runs, or which transactions that are run. These transactions are user-defined. It's a custom script which is generating large amount of wall. This is again used to fill up the wall buffers quickly. I have measured wall IO using pgstat IO. It is a monitoring function in Postgres which can give you disk input output numbers, and it is used for all the backends in Postgres. I have specifically used here for wall sender, measuring disk IO in wall sender. So this is the script that I have used. The main takeaway here is that I have run the benchmark at least 3 times, and between each run, I'm making sure that the OS caches are cleared. Also, a custom script which generates large amount of wall is used in the wall PGBench benchmark, like mentioned. So let us look at a flame graph that shows the CPU utilization of a wall sender. Just to give a recap again, the benchmark used is actually on a setup which sets up synchronous replication between 2 VMs which are in different regions. One is in US, one is in India. This is done so that we can have high network latency. So the TPS is impacted by the amount of time the wall is taking over the network. So here what happens is that we can see the significant amount of time is spent over the network rather than waiting for wall to get sent to the standby. So if we optimize network consumption here, TPS is likely to improve. The time spent to send the wall is about 18.5%, and the time taken to receive it is 21.79%, which is shown by the send function call and the receive function calls respectively. In this particular case, we don't see a lot of overhead from reading from this because it was a 40 KB transaction that I ran with custom SQL and PGBench, and the wall buffers were around 8 MB. So the wall records didn't need to get evicted so fast. So whenever the wall sender wanted to send the wall records, they were available in the wall buffers. Let us look at another flame graph. In this case, I have used a large transaction this transaction is actually the size of the wall buffer, which is 8 MB. So about 43.5% of the time is spent sending the wall to standby here, and about 17% of the time is spent reading the wall from disk. So here you can see libc underscore pread function come up, and that is because of large transaction. A lot of disk read is happening when such a large transaction is being sent by the wall sender. In this scenario, if you optimize disk read, we can improve the TPS. So let us look at the core idea of the performance optimization feature here. As you can see, when we send a wall after getting flushed to disk from master, it results in increase in the disk read and also inefficient consumption of network, especially for large transactions. So the idea here is to send unflushed wall from primary to standby and not wait for the wall to be flushed to disk on primary. This also modifies wall replication protocol to include flush pointer in the message, in the wall message that is being sent. This flush pointer is used by the standby to determine whether it is safe to write wall to disk or not. Wall receiver buffers the wall records until they are flushed on the primary. So until the flush pointer has advanced on the primary, the wall receiver has to buffer these records on its in its buffers. What are the benefits? So quickly, this will result in reduced replication latency, especially when the wall reaches standby before it is flushed to disk on the primary. Wall data flows through the shared memory buffers rather than requiring disk round trips, so reduced disk I/O. There is reduced time difference between transaction flush on the primary and the standby, since the wall records are continuously being sent. For large transactions, this means that most of the transactions' wall records are already sent to the standby by the time the transaction is committed and wall is flushed on primary. So let us look at the wall sender changes as well. So specifically, what is done here is that the wall records that are being sent by the wall sender are divided into wall records that have been flushed and wall records that are unflushed. And wall that has not been flushed, which are after the flush position, are always read from buffers because they are not on disk, and wall before the flush position are actually sent from buffers, and if they are not present in buffers, the fallback is to go to disk. So wall buffers, the wall sender now reads more wall from wall buffers instead of from flush to disk wall files. Wall sender needs to be woken up as soon as enough wall is inserted and not wait for the record pointer advance when the flush has happened. So instead of waking up the wall sender when the flush record pointer has advanced, we are waking up the wall sender after enough wall records have been inserted into the wall buffers. And that size of the wall records is currently 8 KB, because we can't send too small packets also, because that will result in more data being sent over the network, more time the network calls for sending the data are invoked. There are headers attached to each packet, so we can't send extremely small data also. So we wait for at least 8 KB of wall records to be written to wall buffers before notifying the wall sender. So let us quickly look at the benchmark results that I see. So I repeated the same benchmark that I mentioned before, with synchronous replication being set up between VM on primary and VM on which is standby in US. So what you can see here that the custom transaction that I've used is around 40 KB and the wall buffers is 4 MB. And also the network latency is high. And without the patch, the TPS is 125, and with the patch, with the changes of the wall sender to send unflushed wall, the TPS is slightly higher, which is 133, about 5% higher. The wall read IO has also reduced with the patch. So let's quickly look at the wall sender profile after applying the patch, which is to improve sending of wall records from sender. You see that in this, the send and the receive functions take up less CPU time now because we are utilizing the network bandwidth more efficiently by sending smaller packets. You also see that the xlog send physical function has come up here, which means that now we are reading more from the buffers, and that function is getting invoked more because we are reading more frequently now, and smaller chunks of wall is being sent. This could result in net improvement because the network is a bottleneck here, and if you reduce the time spent by CPU over the network functions, if you reduce that, we can see a gain in TPS. So now let us quickly look at the wall receiver changes. Since the wall receiver currently receives the wall records and does not buffer them, it writes these wall records directly to disk. We need a mechanism to hold off writing the wall records to disk until the flush has happened on the primary. The unflushed wall lives in standby buffers and not on disk. So with these changes, the unflushed wall will live on the standby buffers and it can't be written directly to disk. And when the primary's flushed LSN will advance, the standby will then go ahead and write the wall records from buffer to disk. The writing to the wall buffers, reading from the wall buffers, and then writing to the disk file happens in the wall receiver. The wall buffer used is the same as the infrastructure that is used on the sender side, and this is just adapted to work for the receiver context. There can be an alternative implementation at the receiver end as well, in which the writing to the wall buffers and reading from the wall buffers and writing to the file and eventually flushing it does not all happen in wall receiver, and the wall buffers can be shared like how they are on primary. Wall receiver inserts incoming wall into wall buffers. This will eliminate the need of direct IO in wall receiver, whereas the IO will happen in a wall writer process, which will go on and read from these buffers, write and fsync the wall files asynchronously. This will also have an advantage of the startup process being able to read from buffers and fall back to reading from disk if they are not present in buffers, which currently does not happen. Currently, startup process reads from disk to apply the changes on standby. So this can also reduce disk IO in startup. So let us quickly look at the to-do for this feature. As currently, this feature is a work in progress feature. The wall sender changes are showing performance improvements, but wall receiver changes still need to be profiled. So there has to be a implementation and profiling on the wall receivers such that it does not impact the performance gain that we see on the wall sender side negatively. There is one to do here in the design of the wall receiver, which is that this approach relies on the fact that the wall buffers are big enough on the receiver to hold the unflushed wall from the primary. In case the unflushed wall that is coming from primary can't fit in the wall buffer size that has been allocated on the wall receiver, there will need to be solutions. Although this will be a rare scenario, but there will need to be some solutions to handle that. We can either write the records from the wall file, from the wall buffers to a spill file when the flush pointer has not advanced on primary and wall buffers are full on standby. We can notify the sender to pause sending unflushed wall until the wall buffers here on the receiver are available. Or we can have the sender's flush pointer information written in wall records and do not replay any wall until the LSN is greater than the flush pointer LSN. So these are the tasks that are to do in this feature, and this was a short introduction about the feature to improve performance performance of physical replication. I hope it helped you understand more about physical replication and how one can go about improving its performance. Thank you.
All right. That was very good.
And for those of you on the Discord, Rahila is there ready to answer questions if you have any. I just saw her in person at PGConf Dev, which was the annual Postgres development conference that happens in Canada every year. And she gave a talk there as well.
Yeah.
So she's good at sharing her Postgres expertise across a range of conferences, but we're glad she's here as part of Posette.
Absolutely. No, I do love the chat in Discord where also previous speakers are asking about what tests she's used and so on. So looking forward to see more of that.
I put the link up there for those of you who want to give survey feedback to Rahila. I know she would appreciate it. There's also an event survey on the right too. And of course, if you do that, then follow the instructions so you can make sure to get your pair of socks while supplies last. And let's see. I think we have a trailer. That's what the graphic is telling me. So these are all the talks from Livestream 1, which starts off with one of the keynotes from Charles Feddersen and Afan Dar from Microsoft. Full disclosure, I work for Charles. So I've worked for him for a number of years now. So I like the way they explain like what's going on with the teams at Microsoft and all of our work with Postgres. They give kind of like a backstage view of that. But then Boris, who's a co-organizer with you at PG Day Lowlands, he gives a talk, and then it's just an all-star cast from there. So I think we should watch this trailer. Let's do it.
Hi, I'm Charles Feddersen, and in this talk, you're going to learn about all of the ways that we're driving Postgres forward at Microsoft through open source, cloud services, and building amazing tooling for developers and database operators.
Hi, my name is Afan Dar, and in this talk, you will learn about how Microsoft is contributing to the open source Postgres project.
Hello, my name is Boris Mejias, Solutions Architect from EDB, and in this presentation, I'm going to try to show you how to use the JSON data type in Postgres for the best. Because some people have trouble with this data type, they even consider it evil, and they think that the B in JSONB is for beast. But we can tame this data type so that it provides you the best for your database schema, and that you're actually going to enjoy this data type and love it as much as I do.
So hello, my name is Thomas Wondra, and I'm here to talk about random page cost, one of the important configuration parameters in Postgres affecting planning. So if tuning Postgres is part of your job, you might be interested in this talk.
Hi everybody, my name is Adam Vogt. I'm a technical program manager at Microsoft for PostgreSQL. Today I'm going to talk about
fuzzing PostgreSQL and knocking out its door, essentially. You will learn what fuzzing is, how to start your journey with fuzzing, and if it is for you, and how to approach a large complex code base like a database.
Hi, so I'm Chris, and we're going to be talking about Postgres design patterns. So this is a talk primarily for application developers, and we're going to go through a number of design patterns that I've used across 20 years of using Postgres. The talk itself is going to focus on one particular application and all of the different Postgres features that I used to make my life easier as an application developer.
Hey, I'm Pamela, and I'm going to be talking about building a MCP server for your Postgres database. We're going to look at the range of ways you can build MCP servers, from very exploratory servers where the agents can send full SQL queries to your database and do all sorts of things, maybe things you don't want, and then look at fully typed operational servers where you can have maximum confidence in the SQL that's going to get executed, but agents can still get their questions answered. So join me to learn more about building an MCP for your DB.
Hi there, my name is Matt McFarland and I work on Postgres developer tools at Microsoft. This talk is about how our work around the VS Code extension for Postgres management is moving to a new set of tools to support new workflows that are emerging for database administrators and developers who are working on their applications. Please check out this talk if you are interested in AI-enabled workflows and managing your Postgres database with them.
Hi everyone, my name's Christian Miles, and I've been working with graphs and graph databases for about 15 years. My talk is about a Postgres extension called Apache Age that helps you run graph workloads on top of relational data stores. I'll be walking through the graph database landscape and where Age fits in and how it compares with other extensions like PG routing. And then I'll focus on something I'm really passionate about, graph data visualization. When to reach for it, when to reach for Apache Age, and the pitfalls to avoid along the way.
Hey everyone, my name is Andrew Ruffin and I'm a product manager at AMD. This talk is about the Azure infrastructure choices you have and how that choice can improve your Postgres performance by over 60%, including the economics you care about day in and day out. This talk is best for database administrators or IT decision makers who are looking to optimize their cloud footprint when it comes to Postgres.
Hi, I'm Paula Berenguel. Have you ever tried to build expertise across a large organization? I have been doing this for over 2 years, and I will share in this talk what worked well, what didn't work really well, and what are the pitfalls.
Hi, my name is Toyo Bali. I'll be talking about SQL Server and Postgres security model differences. This talk is for someone like me, who is an accidental Postgres DBA, coming from SQL Server world, and we will be comparing and contrasting the security model differences between the two database platforms.
So anyone who hasn't watched that first live stream, this is your cue to check it out, maybe over the weekend.
Yeah, or the talks are already published as well. So you can pick and choose amongst the individual talks. If you're just joining, reminder that there is a virtual hallway track on Discord. Not the same as an in-person hallway track, but actually just as much fun.
Close enough.
So you can just head on over to aka.ms/open-source-discord, and there's a Posette conf channel over there. Let's see, what else do we have for you? Oh, the next speaker. So Nitin Jadhav is a senior software engineer on the Postgres team at Microsoft, and he's going to be talking to us about PG DuckDB in action. And there are 3 demos in this talk where he's going to walk us through how to work with Postgres and analytics with DuckDB on Azure Database for Postgres. But first, at Microsoft, he works on onboarding new Postgres releases, so the quarterly patch releases, the big major releases to the managed service on Azure, and he also handles customer issues too. He's based in Bangalore in India, which is actually where I first met him at PGConf India, which is such a fun conference. And he shares his expertise with the Postgres community by giving talks like this. So let's roll the video.
Hi everyone, I'm Nitin Jadhav. I'm a senior software engineer at Microsoft, and I work for the Azure database for PostgreSQL team. The talk you're going to watch is about PG DuckDB in action, accelerating analytics on Azure database for PostgreSQL. If you have ever wished your Postgres database could just answer an analytical query faster without you first exporting data somewhere else, then this talk is for you. By the end of this talk, you'll know exactly how pgduckdb makes that possible, and you'll see it running live on Azure database for PostgreSQL flexible server. Okay, now let's jump into pgduckdb in action, accelerating analytics on Azure database for PostgreSQL. Here's what I'll cover today. I'll start with what pgduckdb is in just few words. Then I'll spend few minutes on the strengths of Postgres because we are not here to replace Postgres. And then the limitations for analytics, which is the gap pgduckdb fills. I'll then introduce DuckDB and then compare these two Postgres and DuckDB engines side by side. Then go under the hood how Postgres processes a query. And then let's understand how pgduckdb plugs into that pipeline. After that, I'll explain the things pgduckdb lets you do with the help of demo on Azure database for PostgreSQL. And then finally, key takeaways to walk away with. I'll start with what pgduckdb is. pgduckdb is a Postgres extension that brings DuckDB's analytical engine inside your Postgres database. So you don't have to change databases, you don't have to sync data anywhere. You just enable an extension and the same Postgres server now run analytical queries with a columnar vectorized engine. And you can still be on the same reliable Postgres for your transactional workload. It's like bringing the capabilities of OLTP and OLAP at one place. To explain why this matters, let's first spend few minutes on what Postgres is great at. Postgres is the world's most trusted open source relational database, and it has earned that reputation. It's ACID compliant, so you don't lose data, you don't see half-written transactions. It has rich extensibility, custom types, custom operators, and an extension model that lets us build things like pgduckdb. And it has a vibrant open source ecosystem. There are lots of contributors, decades of hardening, and this is the foundation. On top of that, Postgres is a battle tested for OLTP, high concurrency, lots of users, lots of small transactions per second. It has a rich set of indexes like B-tree, GIN, print for very different access patterns. And it runs mission critical applications worldwide, from banks to airlines to your favorite SaaS applications. But it struggles with one specific thing, that is analytics. And it does so for very good design reasons. Let's discuss about this later. Before that, let's first understand a bit about what is OLTP and OLAP. OLTP, it's an online transaction processing, is what Postgres was born for. Lots of insert, update, delete. Each query touches a few rows. Here we optimize for low latency per query and the data stored in a row-oriented fashion. And if you want, and here we want high concurrency because thousands of users hit this database at the same time. And then we have OLAP, online analytical processing, is the opposite. For queries, few queries here, but each query is a huge. Big select with aggregates like sum, average, count. Here we optimize for a throughput, and the data is stored in columnar storage because we usually need few columns out of many, and a single query may scan millions or billions of rows. So I can say that OLTP is like a million single row queries, whereas OLAP is a single query over million rows. Same data but different physics. So when we ask Postgres to do the second job, what actually goes wrong? Three things. One of them, none of them are bugs here. All of them are design choices that are right for OLTP but wrong for OLAP. So the first one is no columnar storage. Postgres reads entire rows even if query needs only few columns out of many rows. Out of many columns. That's a wasted IO on every analytical scan. And there's no vectorized execution. It processes data one row at a time, which means CPU caches and SIMD instructions are largely unused. And there's a limited parallelism. Yes, parallel query exists in Postgres, but it's nowhere near what purpose-built OLAP engines do. None of these are actually showstoppers for your bank balance lookup, but they are showstoppers for an aggregation over billion rows. Let me show you what row IO waste looks like. So here you can think of, we are running select sum of revenue from orders at the both side. On the left we have row based storage, which is Postgres. To compute the sum, the engine has to read every row and all 4 columns, even though we only care about the revenue column. So that's 3 columns of pointless IO on every page, every block, and every disk seek. And on the right side, we have columnar storage for DuckDB. Each column lives in its own contiguous chunk. So the engine reads only revenue column in the compressed batches. So that's why we gain a huge performance here. So this brings us to the DuckDB itself. So the DuckDB is in-process analytical SQL database. Think of it as an SQLite of analytics. It's a small, embeddable, zero config, and ridiculously fast at analytical queries. And it's an open source, and it just in just few years, it's become the default choice for in-process OLAP. Now let's see why. 4 things that make DuckDB special. The first one is it's in process. There's no DuckDB server. It runs in an inbuilt, it runs as a library inside your application. There's no daemon to deploy. There's no port to open. There's no cluster to size. Second, the columnar plus vectorized execution. The data is stored in columns and processed in batches of thousands of values at a time. And third is automatic parallelism. DuckDB looks at your query and it tries to use every CPU core it can. And the fourth is, this one matters a lot for our story, native data lake support. DuckDB can read, write Parquet files, CSV files, JSON, and Iceberg files directly, whether you are on local disk or on Azure Blob Storage. Now let's put 2 engines side by side. Here both are same model, that is relational model, but few different design choices. The first one is workload. Postgres is for OLTP transactions and DuckDB is for OLAP analytics. Storage. Postgres is row oriented, whereas DuckDB is columnar storage. Execution model. Postgres uses the classic Volcano iterator, 1 row at a time. DuckDB processes vectorized batches. Concurrency. Postgres is built for many simultaneous users with MVCC. DuckDB is optimized for one big query at a time. Neither is better here. They're all solving different problems. Then we have parallelism. Postgres has parallel query, but it's bounded, whereas DuckDB parallelizes across all CPU cores. Data sources. Postgres reads tables stored in Postgres, but DuckDB also reads Parquet, CSV, JSON, Iceberg files in the object storage like Azure Blob Storage without loading them. Architecture. Postgres is a classic client-server database, whereas DuckDB is an in-process embedded inside whatever calls it. And that is exactly what PGDuckDB does. So this brings us to a headline slide. So here's the equation. On the left, we have Postgres, which is ACID, MVCC, matured ecosystem, OLTP champion, and the one weakness is analytics. On the right, we have DuckDB, which is columnar, vectorized, lightning fast for OLAP, native Parquet and Iceberg support, and one weakness is no transactions, no concurrent OLTP. Plus those 2 engines, you'll get PGDuckDB. And you keep the strengths of both. OLTP and OLAP in one engine. ACID safety preserved, DuckDB speed for analytics, read Parquet, Iceberg, or Blob Storage from plain SQL. And critically, no new system to learn or operate. It's still the same Postgres your applications connect to. So how does it actually do? Let's look at Postgres query pipeline first. It's a quick refresher, even if you have seen this 100 times. Postgres takes a query, and then the parser tokenizes the SQL, builds a parse tree, validates the syntax, resolves table and column names. And then Planner is a cost-based optimizer. It looks at statistics, decides join order, picks the indexes versus sequential joins, and it gives the plan. And then Executor takes that plan and runs it using Volcano model. It pulls one row at a time through a tree of operators. That row by row pulling is wonderful for OLTP. Fetch the matching customer, return immediately. But for our analytical query, millions of rows passing through that iterative tree one at a time is the bottleneck. Now let's see what pgduckdb does to that pipeline. So it's the same parser here, same parse tree, but the planner is hooked. When parse tree comes out of the parser, pgduckdb gets a chance to look at it and ask, is this an analytical query that I can handle? If yes, then it builds a DuckDB plan instead of Postgres plan and hands it to DuckDB executor, which runs it on a vectorized execution engine and then returns rows back through Postgres to your client. So your client doesn't know anything changed. It's the same connection, same wire protocol, and same SQL. If the query isn't fit, say it's an insert or it touches features that DuckDB doesn't support, pgduckdb quietly hands it back to the Postgres planner, and that's a automatic fallback. You never break, and you just sometimes get faster response. So now let's understand what exactly triggers this hook to actually take over. So there are three triggers. The first one is you set duckdb.force execution to on. From that point on, every eligible select queries are routed to DuckDB. So it first checks whether this can be executed on the DuckDB. So if it is feasible, then it runs on the DuckDB. Otherwise, it falls back to Postgres. And the second, the query reads data lake files, like anything calling read Parquet, read CSV, or read JSON. Such things, DuckDB owns those automatically. And third is, if for any reason DuckDB can't handle a query, then it falls back to the Postgres transparently, as I already explained. There's no errors and there's no broken applications. So what does this let you actually do? So there are three superpowers, and all of them are available on Azure database for PostgreSQL. First one, accelerate your existing Postgres tables. So you set duckdb.execution to on, you run the same group by you have always run, and the DuckDB executes it. Same table, same SQL, but a faster response. Second one, you can read and write Azure blobs directly. There's no copy, there's no ETL, there's no extra service to manage. And the third one, and this is my favorite, that is hybrid analytics. So you can join a live Postgres table, say your customers table with the Parquet files in the blob. Say it's a 3 years of historical orders in the same SQL query. So you can join this live operational data plus the historical archive in one engine, in the engine you already use. So that's very powerful. All right, that's enough of slides. Let's see the demo. So here's exactly what you're about to watch in next few minutes. So there are 5 things end to end. First, I'll provision a brand new Azure database for PostgreSQL flexible server. And second, I'll install the pgduckdb extension on the fresh server created. And then I'll run a tpch queries with a Postgres engine, then run the same queries with the DuckDB engine, and then we can compare. Fourth, I'll read and write Parquet files directly from the Azure blob storage. And fifth, hybrid analytics. I'll join a Postgres table with a blob in a single query. So 3 things to watch here. The query time difference between 2 engines. So whenever I run a query on DuckDB execution engine and Postgres engine, so you can please watch out like the differences. The plan switch, when exactly the DuckDB.force execution kicks in, and the fact that actual SQL itself doesn't change, only the engine changes. Okay, so now I'll start the demo. I will demonstrate how we can accelerate analytics on Azure database for PostgreSQL flexible server using pg-duckdb extension. First, I'll create a new flexible server instance. I'll name the server as pg-duckdb demo. I will now enter the required configuration details such as server version and the administrator credentials. Once the configuration is complete, we can go ahead and create the server. This usually takes some time while the platform allocates and initializes the service. The server provisioning is now complete and our flexible server instance is up and running. Next, in order to use pg-duckdb extension on flexible server, we need to enable it at the server level. So first, I'll update the server configuration by adding pg-duckdb to the azure.extensions parameter. Then we also need to include pg-duckdb in the shared preload libraries parameter. Let's save and restart the server so that the new settings take effect. The restart takes a moment while the server shuts down gracefully and starts again with the updated configuration parameters. The restart is now complete and the server is back online. At this point, pg-duckdb is available and ready to use. Now let's connect to the server using PSQL. Once connected, we simply enable the extension in our database with a create extension query. The extension has now been successfully created. The installed pg-duckdb extension version is 1.1.0 and it internally uses duckdb version 1.4.3 as its analytics engine. In this demo, I'll show two use cases of pg-duckdb extension. The first is accelerating analytical queries by using DuckDB's vectorized execution engine on data stored in flexible server. For the first scenario, I have already loaded TPCH benchmark data with scale factor 5. That includes about 5 GB of data in line item table, around 1 GB of data in orders table, and about 145 MB of data in customers table. Let's now run a few TPCH queries and compare the performance. By default, duckdb.force execution is set to off, which means the query runs using Postgres execution. First, we will run the query using standard Postgres execution engine. Let's start with TPCH query 1. This query performs aggregations over the line item table and scans a significant amount of data, which makes it a good candidate to observe analytical execution performance. While the query is running, Postgres is scanning the rows and computing the required aggregates using its traditional execution model. With Postgres execution, the query completes in about 26.6 seconds. Now let's enable duckdb execution by setting duckdb.force execution to on, which forces the query to run using duckdb execution engine. Running the same query again, you can see it completes in 11.1 seconds, which is 2.4 times faster. That's a nice performance improvement, and importantly, we achieved it without changing the SQL query. Now let's switch to Postgres execution and run TPCH query 13. This run completes in 7.7 seconds. Now we run the same query with the duckdb execution enabled. This time the query finishes in about 4.1 seconds, which is close to 2 times faster. Again, it's a very nice improvement for this analytical workload. Now let's see another example. First, let's switch to Postgres execution. Next, I'll show the query that demonstrates a classical analytical pattern, multiple count aggregations per group. In this query, we filter orders between 1993 and 1996, and then group the results by order priority. For each priority, we compute the number of distinct customer, number of distinct clerks, and number of distinct orders. Queries like this are relatively expensive in traditional row-based execution. With Postgres execution, this query takes 15.7 seconds on this dataset. Now let's run the same query using pg-duckdb execution. Here duckdb processes the data in vectorized batches, which allows it to apply vectorized aggregations very efficiently. This time, query finishes in 2.3 seconds, which is nearly 7 times faster. That's a significant performance gain without changing SQL and without moving the data out of Postgres. Now let's move to the second part of the demo, where I'll show how to read and write Parquet files stored on Azure Blob Storage directly from flexible server using pg-duckdb extension. To allow duckdb to access files in blob storage, we first create an Azure storage secret.
In this step, we register our Azure storage credentials using the create Azure secret function. Once this secret is created, pgduckdb can securely access files stored in our blob containers. For this demo, I'm using a historical stock trading dataset stored as Parquet files in the blob storage. Let's first quickly read the dataset using read Parquet function. This simply verifies that the Parquet file is accessible and gives us the preview of the data. Now let's run a slightly more interesting query. Here we query the same Parquet file directly from the blob storage and retrieve the trend trading entries with the largest price movements. What's important to notice here is that the data remains in the blob storage, Flexible Server does not ingest or load this dataset, and DuckDB scans the Parquet file directly and returns the analytical results. The next part of the demo demonstrates hybrid analytics, where we combine transactional data stored in Postgres and analytical data stored in Azure Blob as Parquet file. Let's start by creating a small Postgres table to represent a portfolio watch list. Let's insert a record for a stock we are monitoring. This table represents operational or transactional data that typically lives in Postgres. Now for the interesting part, we take the watch list table stored inside Postgres and the latest closing price from our Parquet dataset in the blob storage and join them in a single query. That's a result. So we are effectively combining operational database data with external analytical data stored in blob storage all through a single SQL statement. No ETL pipelines, no intermediate ingestion step, and no data duplication. That's a really powerful capability for hybrid analytical workloads. Finally, let's write result back to the Azure Blob storage as a Parquet file. And here we see that the file has been created. And let's also see that the content of the file by reading it using read Parquet function. And here is the data we have written. That's awesome. Postgres can read external Parquet data, analyze it, combine it with external tables, and then write the results back to the Azure Blob storage. We can seamlessly analyze large data sets stored in Azure Blob storage, combine them with transactional data in Postgres, and produce analytical outputs all using standard SQL. That's a powerful analytics with pgduckdb on Azure database for PostgreSQL Flexible Server. And this capability is now available on Flexible Server versions 14 through 18. I encourage you to explore it and see how it can simplify analytical workloads and accelerate analytical queries on Flexible Server. Thank you. Hope you all enjoyed the demo. Now let's wrap with key takeaways. 4 things to note here. One, the first is it's only one database, 2 engines. So Postgres is for OLTP and DuckDB is for OLAP in the same managed server. Second is no data movement. You can query Parquet on Azure Blob directly from SQL. The data lake doesn't have to come to the database and the database doesn't have to come to the lake. And the third one is hybrid analytics in one SQL. So you can club live Postgres tables with the data stored in the blob storage in a single query. And same SQL faster answers. You just set duckdb.force execution to true and your existing queries don't change. Yeah, that's all from my side. Thank you.
All right, and that last slide said that questions and feedback are more than welcome, so make sure that you give that to Nitin. He is also backstage if you have any more questions, so make sure to hit him up, right?
Backstage on the Discord?
Yeah, I feel like that's backstage, no?
Yeah, it's kind of like backstage. I think that
It's kinda
works.
like backstage, yeah.
Sounds cool too.
Yeah. Like
All
we're at a
right.
rock
Oh, you
concert.
want me to advance the slides? You're talking, but I'm moving the slides. Okay.
Let's go. Yeah. Yeah, as said, he's asking for feedback. Make sure that you give our speakers feedback. They really do appreciate it and can make their talks even better for you next time. So make sure you do that. And I mean, there's something in that for you as well. And you have some time to do it still too. If you're just like, no, I want to catch this next talk, I'll give the feedback later. You can do that. Just make sure that you give feedback to the speakers and to the organizers of this wonderful event as well, please.
Deadline Monday, 22nd, 11:59 p.m. Anywhere on Earth. Got it. Okay. Oh, you got to talk about this part.
Oh, you feel awkward talking about your podcast.
No, I'm not awkward. It's just that I could get us off schedule. Like, I love all of these conversations with these amazing guests so much that I could talk about it for a long, long time. And it's not about me, it's about them and their stories, their experiences working with Postgres and giving everybody that backstage view into like why people who work with Postgres do what they do. So I'm going to stop talking now and let you do the talking.
Yeah, people that are contributing to Postgres are mentoring new people to come to the Postgres community, like anything that has to do with Postgres. It's a really enjoyable podcast. Having been on it, I know that Claire and the team put a lot of thought and time into this as well. And it's always a very, pleasurable conversation. So I really enjoy this. There's plenty of episodes. So, the best. Yeah, I mean, you should have watched and listened to all of them, I guess. But the best, second best time to start is, right after this live stream ends, I guess.
So yeah, I'm jumping over the names, but if you go to talkingpostgres.com, you can see all of the names, and there are different topics and different areas of focus. So lots to listen to. I think it's time for our next talk.
Yeah. So Chun is joining us as a software engineer who's specialized in cloud architecture and observability. Also a proud member of the .NET Foundation since 2019. Enjoys helping engineers bridge that gap between sort of infrastructure metrics and application performance. He also develops an open source library called SNA to help developers model simulation scenarios using .NET as well. So he's saying many developers run Postgres on burstable cloud instances to optimize costs, which of course is fair enough, we understand. But in doing so, you could introduce some performance risk as well. And of course, our speaker wants to help you avoid that. He'll demonstrate how to model the saturation point of a throttled Postgres instance without the need for expensive load testing tools. So yeah, let's look at that.
Hi, I'm Chun from .NET Foundation. Have you ever deployed your Postgres database and other cloud services to the public cloud service? So sometimes you may have this question. Can I actually performance testing our infrastructure before we actually deploy it on the cloud? Well, today in my talk, I'm going to show you how we can use discrete event simulation to do the shift left performance testing on our infrastructure before we even deploy it on the cloud. So let's start with seeing how we can use discrete event simulation to model our Postgres database performance degradation on Burstable cloud instances. Before we start, let me explain a bit about Burstable instances. So you all know about cloud compute, right? So the general use of the cloud compute is that you have the 100% of CPU credits that you are able to use. However, in Burstable instance, there's this thing called the baseline CPU. So when your usage is below the baseline, you are able to accumulate your CPU credits. Because of this, when you need more and excess CPU credits, for example, during Christmas or during New Year, you expect more volume to join in to retrieve data from the database. At that time, you will expect a burst in your CPU. So those saved CPU credit can be applied at that time. So this is the selling point of Burstable instances. And because you are having a baseline, you actually get 20 to 60% cheaper than the fixed performance instance. So it's perfect for variable workloads, right? Because on the normal days, you don't need so much CPU credits and you can save them and apply them when you need. It sounds good. So actually, how does it work? So if you are working with API limit, you will know this thing called token bucket algorithm. Okay, so let me show you what it looks like in a graph. So you start with some credits available in your instance. Then you run your workload. So when it hits 0, then your CPU will be throttled. So at that time, you don't have excess CPU credits. So you will run your workload at the baseline. And at this time, the server will slowly recovering your CPU credits because you actually only use up the baseline and you earn a bit of the CPU credit. So what is being left over will be your net credit gain. So over time, over some time, your CPU credit will be above the CPU baseline. So when the Christmas or New Year come and it hits the burst mode, that's when you can use 100% of your CPU and you can run a lot faster instead of being throttled. And at that time, those CPU credit being saved will be used up until you hit the 0 CPU credit. Then you go repeat again. So this is the so-called the token bucket algorithm. So in short, you earn credits continuously over time, whether you are being throttled or you are bursting your CPU. And you burn credits when you are using CPU above the baseline. And when there are excessive credits available in your savings, you are able to burst to 100% CPU. And when depleted, you are being throttled to the baseline. So for example, on Azure B2MS, your base CPU performance for that is 30%. And you earn 36 credits per hour and burns 2 credits per minute at burst. So these parameters, these values are very important later when we use discrete event simulation to model our infrastructure. So how do you get this kind of values and parameters? Well, there's a documentation on Microsoft Learn having listed all the Azure B Series V1 CPU parameters. So as you can see, for example, the B2MS that we will be using in our subsequent demo, yes, 30% of base CPU performance and initial credit is 60. And it will bank in CPU credit per hour at 36. So when your CPU is throttled, and so you will be using less than 36, then the excessive amount will be saved. And how much you can save? Well, of course, it's based on the size of your instance. If it's B2MS, you will be at the maximum of 800 x64. So if you would like to know more about this table, you can take out your phone, scan the QR code over here, and you can find out more about this information. Okay, so what's the problem of this? It sounds good, right? I don't need so much CPU when it's not Christmas, when it's not New Year. So what's the problem? Well, when CPU credits deplete, we see that on the instance, the database throttled to baseline CPU. So the query time increases significantly. It can be 5 times or even worse. But Progress doesn't know it's being throttled because it's at the CPU level. So slow queries will then hold the connection longer. So when having more visitors coming into your apps or websites, the connection pool will be exhausted. But it can get even worse than this. So when the connection held longer, as we said just now, the connection pool saturates, and then more visitors coming in, then that is the time when you see, wow, P99 latency spikes and app layers times up. So this is when the PostgreSQL start to reject the connection. So at this point, maybe your Grafana alert will start to send you alarm that saying you have a production outage. But it actually gets worse than that. It doesn't mean the Postgres just start to reject, but the health check will fail. And then the orchestrator on Azure, for example, will start to restart the database. And because of this heavy restarting, it will burn the remaining CPU credit. So actually, when you will go into the death spiral, where it will keep on burning your excess CPU and you can't recover. So manual intervention will be required at this to break the loop. So this sounds very serious if you didn't know how the token bucket algorithm works. So there are a few solutions to this. So one is, of course, use over provision. You just don't use B series entirely. And you just pay for the normal, like the general purpose instance. Well, it works. Actually, it's a very safe option. But when your business scale up, then it will be very expensive. You're actually overpaying. Second way is that you try to find out what are the configurations, what are the setup that you need, and then you do a load test. For example, you run Grafana K6 on it, and then you monitor over the time. But this is wasting a lot of time. If you need a week of data, you need to run your load test for that week. So that's why I would like to introduce you another way, which is called simulation. So we use more math to model the token bucket algorithm so that we can get good enough result in a very fast speed. So the simulation approach is like this. So in our demo today, we will use simulation to model the credit mechanics, the CPU credit mechanics, and then the queuing behavior. So simulation will act as a filter in our case. Okay, so just to clarify, what I mean is that simulation is a filter. It's not a total replacement for load tests. So it helps you to, let's say you have 100 configuration that you think your setup can be done, but you are not sure which one is the best. So simulation helps you to run all these 100 configuration and find out the best, for example, the best 3 instead of like best 100. Then you load test the final 3. Then you find out the best one. So this is the use case of our simulation here. So why are we using discrete event simulation, or we call DES? So DES models system by following each event step by step. So what do I mean by that? For example, imagine you're watching a movie. You are not interested in the heroes going to take a shower, having a dinner, or just sleeping for 10 hours. That doesn't add anything to the movie, right? What you are interested is the event, the fight, the key happenings. So discrete event simulation is the same. So it only models the event at each particular time, which is important to the simulation. So when we chain out this event, we form a list called the future event list. So if you are already aware, the token bucket algorithm that we showed just now are actually a graph of events. So when your CPU hit 0, it's one event. When your CPU recover, it's also an event. So in discrete event simulation, we have 3 things. We call it the generator, the queue, and the server. So generator, in this case, in our demo, we will be using a distribution to random generate the visitor, to simulate the visitor incoming. And then the DB connection pool, in this case, will be the queue. Of course, the burstable instance that we model against is the server. So with these elements, we can actually model using discrete event simulation. So last year, I learned from my professor in National University of Singapore, Dr. Lee, and come up with my own open source library for discrete event simulation called SNA. It's done in C# and the latest .NET framework, which is .NET 10. Of course, the latest now is .NET 11. But yeah, the general purpose is .NET 10. So with this library, I'm able to model what we discussed just now with the MMCK-Q. So it provides deterministic logic for the stochastic inputs. And as you see just now, the table, right, with a lot of baselines and unrates. So I just put them in as the input parameter for the simulation. And then I can configure. And then I see what is the output from the simulation. With that, I can validate against the queuing theory prediction. If you are interested, you can scan the QR code over here, which will lead you to the GitHub repo of my project. So back to our question earlier. So how do we know at what point our specific workload transition from bursting to the death spiral that we discussed earlier? We need to know like, so imagine now you don't have simulation. What you can do is that you set up this burstable instance with Postgres on Azure or AWS. Then you let it run. Then you do a load test on it. Then you monitor over a few days just to get the result. So how can we shorten this? And this is how we use the simulation. And in fact, I can get the result, which I will show next in just 1 minute. Actually less than that. So how do I do that is that, again, it's a similar graph, but this shows how I model the credit token bucket algorithm. So with the credit available starting point from the left, then the query starts. Then my code in SNA will check whether there's a sufficient CPU credit or not. And then if it doesn't have enough CPU, this will go to the baseline mode. But if you are still burn credit but at the baseline rate, then it slowly recover by earning the excessive credits. When you have enough CPU, then it will go to the burst mode with 100% CPU. That is when your database is able to perform at its highest rate. So it's the same graph, and we model it in C# code. So the result is this. So as you can see on the graph here, so the credit start is 60. If you still remember the table just now, B2MS start at 60. Then it has a linear depletion as the burst usage exceed the earn rate in our demo here. So as you can see over time, after like about 20 minutes, the credit will hit 0. Yeah. And then it will stay at 0 forever because it can't recover. So from this graph alone, you will see your setup actually has this death spiral issue. So you can easily find out before you even set out on Azure through simulation. So what happens when the credit hit 0? We can also find out through simulation is that there's a 5 times degradation for the CPU bound queries. So production cascading effects are getting worse. So this is why database is up. Sometimes doesn't mean the database is actually working. So at this point, I didn't even set up anything on my Azure yet. I just use mathematics to model the entire behavior through simulation. Another question that we commonly have is that, how big should my connection pool be? So some people have this idea of getting as big as possible or just increase the connection pool size when your database is slowing down. So, but is this assumption or is this behavior good? Can we do shift left testing on this kind of question as well? Well, the answer is of course yes, otherwise I won't put in the slide. So yeah, the discrete event simulation with my SNA library will be used in answering such questions. So as I shared just now, so common advice will be like just having pool size of 5, of 10, of 50 or 100. But they have some assumption which may not applicable to your use case. So 5 can be working for a startup database, but may not be working for your popular enterprise solutions. So how do we simulate this? So in this demo, we can use simulation to find the smallest pool within the 5% of optimal latency. Okay, so when I run the demo with the simulation code, what I get is this graph as you can see over here. So we have, I run the test for pool size of 5, 10, 20, 50, and 100. And it's surprisingly, after the 10 pool size of 10, actually the improvement is not a lot. So we found that the optimal for steady load in our demo actually can be handled by a pool size of 10. So when you add more to the pool size, it actually doesn't help much to the latency. It will always stay after 55, 56 milliseconds. So this is the coolness of doing modeling and simulation to find out the results before you actually deploy. So you may ask, does this only happen for Azure? No. As I shared just now, Burstable instance is very common in all the cloud providers. In AWS, it is called the T series. But across the different cloud providers, they have different minor difference among them. So for example, I actually did AWS modeling on this also. For AWS, the initial credits of the T series always start with 0, unlike the Azure, which is 60 or some non-zero numbers, depends on your size. And in AWS, there's this thing called the T series. So it's called the unlimited mode. So unlimited mode in T series means that instead of depleting your CPU, when you hit the 100%, when you burn out all your CPU credit, all your savings, it will still allow you to continue to run your database at 100% of CPU. But it will charge you more with the excess CPU. So this is the difference between different cloud providers. And of course, the baseline percentage is kind of different between different cloud providers. But anyway, the fundamental, the math, the principle will all stay the same because same approach works across all cloud providers as long as they are using the token bucket algorithm. So you may ask, is it overkill? Yeah. So last time when I shared this with AWS community, so they asked, are you overdoing something which is you can get easily with guessing? Yes, of course you can just guess like the pool size, connection pool size, or you can just guess when your CPU will hit 0 and so on. But that only works if you are working in a small team and a small infra where you can change your configuration very fast. If you work in an enterprise solution with like 50 or hundreds over instances, it is very dangerous and very costly to just use your assumptions to determine what is the connection pool size to use. And it is even more costly if you actually deploy this and you use load tester to run the load test to hit your production or UAT database, because that will actually be charged by the cloud providers. So over provisioning is never a small method for those enterprise solutions. So it depends. If you have a very small scale of database configuration, of course, you can just guess and you can trial and error to fix it. But for a large scale of enterprise simulation, modeling is always the best way that it can give you answer in a very fast manner. So what I shared just now is that we have seen how we model the CPU credits as well as the queuing. But I did not model the IOPS throttling, the network, and the storage latency. You can do so by checking out my code and adding more to make it more robust. But what I show you is only the CPU credit issues. One more thing. So when I was preparing for this presentation, I actually add one more very important things to our SNA library, which is called the observability. So with the OpenTelemetry integration, now when you run your simulation over different configuration, you can actually see the performance on your dashboard. For example, Grafana dashboard as shown over here. So yeah, you can see the performance cliff, and you can easily get your graph out real time. Yeah. So today's conclusion of this sharing is that instead of like guessing, we do performance testing on our infrastructure by shifting left using discrete event simulation. So before simulation, you just guess or you just test in the actual cloud environment. But now you can do it locally. You can run as many tests as you want, and you can identify the failure points before it happens on the cloud, which will cost you money. And instead of running it for days or weeks to just see the pattern, you can now narrow it to just a few seconds or 1 minute. And it gives you a data-driven results to help you better configure your infrastructure on the cloud. So yeah, thank you very much for the time attending to my talk today. I hope it's helpful because discrete event simulation is not something that you hear in the talks. It's kind of academic, but I found it can be very useful in the real life production work as well. So if you would like to find out more, which actually I posted all my demos code on this repo, you can check it out. And you have more questions to me after this event, feel free to contact me on LinkedIn, and I'm happy to chat with you on this matter. Thank you very much.
So a little academic maybe, but I actually really enjoyed this topic. I have a little bit of a connection to the load testing topic. I used to work for Grafana K6, which I don't want to say got an honorary mention in this talk, but got a mention anyhow. And I will definitely try out this tool by Chun Lin, especially after you mentioned that there's an integration with OpenTelemetry for observability. So super interesting talk, this one. Really
There's a
enjoyed it.
connection between Grafana and the Netherlands, isn't there? There's an affinity there?
Is there?
I don't know. I thought there was, maybe.
I mean, there is some Dutch employees there, of course. Yeah, for sure.
All right. Well, I really appreciate it.
Oh, did you want to like reference the orange color of the logo? Is that the thing? That would work.
Oh my goodness. Okay, so for those of you just joining, speakers appreciate talk feedback. So we're dropping the URL on the screen really quickly before we move on to our next talk, with a reminder that you can get socks for submitting the surveys, and the deadline is Monday, the 22nd of June, 11:59 p.m. anywhere on Earth time zone. So, oh, and if you want sticker swag, just head on over to the Discord where you can ask speakers questions as well. There's a lot of interesting conversation there. So it's worth dropping by. I actually, before we introduce our next speaker though, someone somewhere, I'm paying attention to a couple of different chats, described what you're doing today, Floor, as
yeah, that's so good. Yesterday I was trying to explain, like what we're doing here today, Claire, and she mentioned, oh, so it's like DJing nerd talks, and I was like, oh yeah, well, I guess that's a good summary of Posette.
Awesomely useful Postgres talks. But and speaking of awesomely useful Postgres talks, let's talk about Hadi Kiran for just a moment. He's a database engineer. He's got probably almost 2 decades of experience in this space. He's the founder of a company called Open Source DB, which is focused on anything and everything Postgres related. So database administration, enterprise implementation, security, backup and recovery, performance, you name it. That's what Open Source DB is focused on. He's also a distributed Postgres evangelist at PG Edge. And he's involved in a lot of Postgres community event organizing in India. So I saw him earlier this year at PGConf India, which was in Bengaluru, where he was one of the people involved in organizing that. And he's also involved in Hyderabad Postgres Days, which is happening on August 20 through 21. So not that far into the future, obviously in Hyderabad. So he does a lot for the Postgres world. And this talk is on the past, present, and future of logical decoding and replication in Postgres. Let's roll the video.
Hi everyone, my name is Hari Kiran. Today we are going to track the full arc of logical decoding and replication. We'll go from its earliest building blocks in PostgreSQL 9.4 all the way to the multi-master distributed future that's being actively built right now. Let's dive into past, present, future of logical decoding and Postgres logical replication. This is an important topic. Quick one, who am I? 20 years with databases and the last 5 years building a Postgres startup. So yeah, I have seen both worlds. I'm the founder of Open Source DB and I love building communities. Hyderabad Pug, Vizag Pug, and Postgres Women India. I speak at Postgres conferences, teach as an adjunct professor, and I'm a strong open source evangelist. Before this, I had stints at General Electric, Optum, Oracle, Second Quadrant, and EDB. So yeah, I have looked at different ecosystems. So if I sum it up, Postgres, community, and startups, that's my zone. Now let's look at what we will cover today. Right? Here's our roadmap. We will start with the past, where logical decoding came from, how extensions like PGLogical Outlook shaped the ecosystem before native support in PG10 existed. Then we will move into the present, looking at native logical replication features from PG10 through PG18, including CDC pipelines, real-world deployment patterns. After that, we will look at the future DDL replication, the multi-master architectures, and what the community is building for PG19 and beyond. And woven throughout, we will do an architecture deep dive into the internals wall, output plugins, and replication slots, so you don't just look at these features, but how they work under the hood. Let's get started. You would have seen, physical and logical replication. Before we dive into the history, let's make sure we are all on, the same page with respect to the replication topologies and the architecture. The logical replication actually is, and how it differs from physical replication. Everybody would have seen physical replication, right? It is shipping the raw wall bytes from primary to standby. It's an exact block level copy, which means standby runs the same major Postgres version. You replicate the entire cluster, and the standbys are read only. In contrary to the logical replication, right? It slightly works differently. Instead of copying raw bytes, it streams the row level changes based on the replication identity, typically the primary key. This gives you some really powerful properties. You can replicate across different Postgres major versions. You can selectively choose which tables and even which columns of rows, thanks to some of the row filtering features that were introduced in the latest releases. And critically, it opens the door to multi-master setups where multiple nodes can accept writes. The important thing to know is that both mechanisms can run concurrently in PostgreSQL. You can have a physical standby for HA, you can have a logical replication for CDC or cross-version migration on the same cluster. They can coexist. And moving on, let's look at the logical decoding, how it actually works under the hood. This architecture is fundamental to everything else we discuss in this 20 odd minutes. It starts with the wall. When you set wall level is equal to logical, PostgreSQL starts writing additional information into the wall that allows it to reconstruct all the logical changes, not just the raw bytes, but the actual row level inserts updates and the CRUD operations that are happening on the primary server. That wall data that passes through the logical decoding layer, and this is the engine that reads the raw wall records and translates them into a stream of logical change events. It handles transaction boundaries, the snapshot management, and the ordering guarantees that make replication super reliable. Next comes the output plugin, right? This is the output plugin where the decoding changes get formatted for consumption. Postgres ships these the output plugin called as PG output, and this is the default plugin used by the native logical replication. But there are alternatives like wall to JSON, which formats the changes as JSON, which is popular in the CDC pipelines. And the test decoding is another popular plugin, which is useful for debugging the changes that are happening on the primary systems. Finally, thanks to the 9.5 feature, we had something called as replication slots. This is the persistent mechanism. A slot tracks every wall file, right? Each consumer has read up to that wall stream or not. If a consumer disconnects and again reconnects after a planned or an unplanned outage, it picks up right where it left off, right? Slot persists across server restarts, right? Which is the powerful feature that some of the planned outages can have, right? But it's also something you need to monitor carefully, right? Because an active slot will prevent all of your walls to be not cleaned up, which will again bloat your storage. We'll come back to that slots aspect in our performance section. At the end of this pipeline sits the subscriber, right? The target logical subscriber. That could be another Postgres instance, or it could be an external CDC consumer like Debezium, feeding into Kafka, which has been a really important use case in the CDC pipeline ecosystem that we learned. Now let's look at the past, right? What was the foundation that was laid as part and parcel of Postgres 9.5? Now let's rewind a decade or a decade and a half, right? Postgres 9.4 was the first release where there were the building blocks for logical replication, right? That introduced into the core of the Postgres. And Postgres 9.4 gave us 3 critical primitives, right? First, replication slots that persist the tracking mechanism I just described about. Second is the replica identity for the table level parameter that controls what information gets written to the wall for updates, deletes, and the CRUD operations. By default, Postgres uses primary key, but you can also set it to a full by using the replica identity and write the entire old row or nothing. And then the third is the logical decoding API itself, right? The framework that plugs that can use the entire decoded changes and then push it across to the target instance. But here are the things 9.4 gave us, right? The API, but not the complete feature set. There was no built-in create publication. There was no create subscription, no publication on the source, and subscription on the target side, right? We always needed an extension, like I mentioned, PG logical and PG logical output. That's where the extension PG logical came up, right? And then it built the full publish and the subscribe model, and on top of the 9.4 logical decoding API. It supported row filtering, conflict detection, and was the technical foundation for the entire bidirectional replication, right? The BDR 1.0, which was a completely open source extension we had, right? In 2017, Postgres 10 brought native logical replication into the core with publication, subscription, syntaxes, right? That's where we say create publication, create subscription. We will see an example in one of our slides, right? This was powered by the PG output plugin. This feature to a first-class Postgres capability. Now, let's move on and see the evolution from Postgres 10, where we introduced the first native logical replication till the current major version of PG 18. One logical replication, indeed, landed in core of PG 10. The community just did not stop, right? Every subsequent major release has added meaningful improvements. And this slides gives us the entire timeline. What happened on PG 10, what happened in 13, 14s, 15s, and so on and so forth, right? But let's just double click on PG 10. It gave us the basic publish and the subscribe model, right? And then PG 11 added the truncate replication. Previously, truncate was not captured by some of the logical decode, right? Now, PG 13 was important because it introduced the logical decoding in progress, right? Now, the in progress transactions. Before that, very large transactions. We are aware that some of the applications perform large transactions would only be decoded after the commit, which means there is 1 million records that are being processed on the source side. You could only look at decoding them and sending across to the logical replica after the commit, which could cause massive lag spikes, right? The real game changer came in PG 15 and 16, right? 15 gave us row and column filtering finally, right? Now you could just publish only a subset of the rows, right? Now with a where clause. And you would appreciate the fact that off of the entire 10 million table, you want to broadcast only 1 million or a few hundreds of case of records and choose exactly which columns to replicate. PG16 added parallel apply, right? Multiple workers processing changes currently and concurrently. Binary node of the initial table copy, which is significantly faster. And then another important feature was the failover of replication slots that came in 70, making logical replication viable for HA architectures. And in PG 18, which shipped in last September 2025, brought us the detailed replication support, conflict detection and monitoring, and parallel streaming as the default. Each of these releases, when we look at some of these blocks, right, the foundational blocks from the 9.4 world to the 10 to the 18, right? So we've been building towards making native logical replication truly production ready, right? And I'd argue that as of PG 18, we are now far more ahead of the curve when it comes to the replication. Now, let's look at some of the 15 and 16 production-ready replication, right? Let me zoom in on two important features that I think were the biggest inflection points, right? Row and then the column filtering in PG15 and the parallel update, right? And then, most of you all have seen the new GUCs that were introduced, right? Max parallel apply workers per subscriptions. Row and column filtering, fundamentally changed what's practical with logical replication. Before PG15, a publication was all or nothing, right? You publish the entire table. Now you can write something like, I will create a publication for a specific table called orders, where region is equal to APAC, and only APAC region orders get replicated to the subscribers that are there in place, right? Column lists, similarly, you can choose to publish only specific columns. This has huge implications, assuming you are looking at a multi-tenant architecture. Data sovereignty compliance is a very important feature or the offering that some of the platforms do. And simply reducing the bandwidth and the storage costs of replication. If you are running a SaaS platform and you are in need to replicate customer data to regional clusters, this is the feature that makes it practical without having to reconstruct your entire schema. And then another feature, parallel apply in PG16, addressed the major bottleneck of the throughput, right? The throughput between the source and the target. Before 16, a single apply worker processed all the changes in a sequential manner, right? If your publisher had a high write rate, the subscriber would fall behind, naturally, because the velocity at which the changes are happening on source versus how they are applied. With parallel apply, Postgres can use multiple workers per subscription, right? That's the GUC that I was referring to. Applying non-conflicting transactions in a concurrent way, right? Combined with binary mode for the initial table synchronization, which skips the text conversions step. PG16 dramatically reduced both initial sync and the steady state of the replication lag. And moving on, right? What is the latest advances that we have made in the PG17s and 18, right? Continuing the momentum. Failover replication slots in PG17 solved a real operational pain point. Before this, if your primary failed over to a standby, your logical replication slots were lost, right? Subscribers wouldn't disconnect, potentially needed a full resync. PG17 allows slots to survive failover, and the new PG create subscriber utility, right, makes it pretty straightforward to convert a physical standby. And physical standby, you don't need any downtime per se, right? That physical standby was transformed into a logical subscriber, which is incredibly useful for a zero downtime major version upgrades. Now we'll talk about that zero downtime upgrades in a moment. And then in PG18, the headline for logical replication is the conflict detection and monitoring, right? The new PGStat subscription stat views gives you a per subscription counters for different conflict types, the insert conflicts where a row already exists, update conflicts where the origin differs, missing row conflicts. This visibility is essential if you are running any kind of multi-node topology. In PG18, it also lets you replicate stored generated columns, which was a pain point for most of the database models. When your subscribers are non-Postgres systems, they can't recompute those values, and create subscription now defaults to parallel streaming mode, right? So you get better throughput throughout the out of the box without any manual tuning. Now moving on, native versus extension based. This is the comparison that I wanted to look at, right? So given all the improvements in core, right, and I wanted to touch upon extensions like PG Logical, Spark, and BDR. Where would they fit in, right? But look at some of the advanced features, right? DDL replication, just arrived in PG18, right? Extensions like BDR, PG8, Spark extensions have had that auto DDL for a while, right? And conflict resolution in core is still, basic level of monitoring, gives you detection and monitoring, but not the sophisticated last writer wins, first writer wins, and some of the conflict handlers that the PG Logical and Spark extensions provide, right? And then the big one in PG18 is the multi-master replication, right? Native Postgres still does not support it completely. PG Logical has had a partial support. You can set up bidirectional replication with some conflict handling. BDR and Spark offer full multi-master mesh topology, right? Bottom line, if you look at the use cases, they are straightforward, right? If you have a pub sub replication, CDC, or a cross version migration, right? Native logical replication is now excellent, right? You need multi-master, advanced conflict resolution, or automatic DDL synchronization, in complex topologies. Extensions still lead you there. Now, let's look at the use cases, right? The change data capture. Right? Let's talk about this super important aspect, right? The CDC. This pipeline is probably the most common production pattern. Your Postgres database publishes changes through a replication slot. Those changes are consumed by a CDC pipeline like Debezium. Right? It's a popular option which feeds into a streaming platform like Kafka. From there, downstream consumers can push it to a data warehouse, analytics engines. ClickHouse is a good example, which can consume those events. Right? Why logical replication is the right foundation for CDC? Right? It is fast, minimal performance impact. Right? Before we were reading from the wall, there's no trigger overhead, right? Your OLTP performance isn't affected by the CDC, right? Secondly, right, transactional consistency. Changes are delivered in commit order. You never see a child record before its parent, right? So the ACID compliance, you will never see a partial transaction. This is the guarantee that polling-based or time-based CDC approaches simply can't provide, or it cannot give you that compliance. Third is the flexible output formats, right? The PG output plugin gives you an efficient binary format. Vault2JSON gives you JSON and easy parsing. You can write even custom output plugins for specialized needs. Spark is a good example. And the last one, the zero downtime migration. Now set up a logical replication to new Postgres version, let it catch up, the cutover lag is zero, combine it with the PG create subscriber. The workflow is now remarkably streamlined. Now let's look at the the quick setup that we can do with a simple set of commands. On the publisher, you need 3 configuration parameters, right? Wall level, and then your max wall senders and the max replication slots, right? The default values are good enough for max replication slots and the wall senders. You got to change only the wall level from replica to logical. On the subscriber side, it's a single SQL statement, create subscription, pointing at the publisher's connection string and the publication name, right? Postgres handles initial table syncs and then starts the entire streaming changes from your source to the target. Now look at the more advanced SQL example there, right? Which is 15, PG15. You can create a publication with row filter, like I said, right? You're saying region is specifically US. You want only those matching rows broadcasted, and then you can specify exactly which operation to publish, whether you need an insert, whether you need a delete, or you need any combination of them. And with 18, you can now monitor replication health programmatically by querying PG stat subscription stats. right? These conflict counters are, I mentioned earlier, conflict insert exists, conflict update missing, they are all right there in the system view, right? Now, let's look at some of the real world patterns that are emerging, right? Let me quickly walk you through 4 production patterns that we have been seeing where logical replication is making a huge difference. Zero downtime migration upgrades. This is probably the most common use case you set up, and logical replication for your PG16 cluster to a PG18. Once the subscriber catch up, you are good. Right? You can do the upgrade. And the PG upgrade brings in that uncertainty in a large database that could be avoided. Multi-region data distribution, right? It can replicate subsets of your data to regional clusters. And the real-time analytics pipeline, we talked about the CDC ecosystem, right? From your OLTP systems through the Debezium Kafka of ClickHouse, right? Now, database consolidation is an inverse pattern. Multiple source databases, each published to a single subscriber for centralized reporting and analytics, right? So that's one of the important stuff, I would say. Now, moving on to the performance tuning and the gotchas that I wanted to double click on, right? On the best practices side, prefer logical identity using index over replica identity full, right, on the large tables, because you are going to be constructing a lot of full writes. Enable parallel apply if you are on PG16 and later, right? No, that the GUC that I referred to, right? And monitoring the replication lag continuously with pgstat replication. The max slot keep wall size to limit how much of wall an inactive slot can retain, and use binary mode for the initial table copy. It's significantly faster than text mode, right? And then missing primary keys will break the replication updates and delete. So any changes that are being happening for the schema needs to be applied onto your logical replicas. And then long running transactions on the publishers block slot advances. Now let's move to the future of it, right? The distributed databases, the multi-master system, right? The holy grail of many Postgres users is multi-master replication, right? What you see on is slide is 3 Postgres nodes geographically distributed, each accepting both reads and writes with changes flowing through bidirectionally between them. Like this is active replication. The key capabilities needed for this are active writes every node handles, and the reads and writes simultaneously. Right? Automatic conflict resolution where 2 nodes update the same row concurrently. The system needs a policy. Last writer wins based on timestamps is the most common one we were looking at. Right? Who is building it today? PGEdge with their open source Spark extension provides multi-master replication for community Postgres. EDB is BDR, and the most once in 5 nines availability, and Postgres community itself is contributing foundational pieces, conflict detection in PG18, the sequence replication, failover slots that are building towards the future in code. Right? And the horizon, I would say, right? What is there in PG19 and beyond? Google has been contributing significant work on automatic conflict detection. Sequence replication is maturing. A structured conflict log, a dedicated table for conflict events. Parallel PG dump improvements combined with logical replications will make that initial data sync in large migrations really faster. And the big question, will active replication land in core? The honest answer for me is the community is building towards it incrementally. Each release adds another foundational piece. PG18 added conflict monitoring. Future releases may add more and more conflict resolution policies. Now, looking at the key takeaways. The key takeaways that I would say are the 5 important ones. What I have here is logical decoding laid the foundation, native replication in PG10, and extensions like PGLogical, Spark, and BDR pushed the boundaries. And then the fourth and then the fine important pieces are the CDC pipelines and the future of distributed databases, the active PostgreSQL that is being built into the open releases, right? And that brings about the last of my slides. Now that's everything I have got for you. Thank you so much for spending this time with me at Posette 2026.
No, thank you, Hari.
We're live again, aren't we?
We are. Correct.
You it's just, I don't know. It's hard to keep track. You're kind of like so deep in paying attention and watching a talk, and all of a sudden, like, wait a minute, he stopped. Yeah. All right. Now Hari's involved in onboarding new community members, right?
Yeah, a lot. Yeah, you were introducing him, and I was just like, yeah, those things, and then like a bunch of other stuff too. Like, there's just otherwise the intro would have been too long, probably too. I mean, Hari and I are on the Code of Conduct Committee together as well. Yeah, and I just really appreciate Hari for all of he does for the community, onboarding code contributors, but also other community builders. You mentioned PGConf Dev a couple of times on this stream already. He joined me on a panel discussing all of the ways that volunteers can get involved with the project, and with Cornelia too, in a sort of working discussion following that panel at PGConf Dev, and Cornelia is of course in backstage with us, in the true backstage, not in a Discord.
She's on the Discord too.
Oh, where it's too.
She's in both backstages, I guess. Not that
Everywhere.
I'm correcting you. I'm not correcting you, Floor. That's not happening.
No, you're just giving an addition, more information. That's good.
Being pedantic. Okay, we've got a trailer next. So we are going to look at some short snippets from some of the speakers. Now, of course, there are speakers who are backstage on Discord right now, and so feel free to pop over there if you have any questions. And of course, we always put the survey link up at the end. But then we want to roll the Livestream 2 trailer. Now, remember that Livestream 2 already happened. You can still go watch the replay on YouTube if you want to watch the whole kit and caboodle with all of the discussions and transitions in between the talks, or just go watch the published talks on YouTube too. And here's what you'll find.
In this keynote panel, we're going to be talking about what actually happens as we approach the annual Postgres feature freeze.
You'll get the inside scoop on how Postgres contributors develop all of your favorite features coming in Postgres 19.
Why do some Postgres patches make the cut while others miss the boat, or even get reverted in the end?
Join us to hear from 4 experienced Postgres hackers and committers who have had years of fun with Postgres and experience with patches both making it and missing the boat.
Hello everyone, I'm Marco Slot, and my talk is going to be about PG Lake, which is an open source extension for connecting Postgres to the wonderful world of data lakes and lakehouses. So I'm going to talk about how you can use PG Lake to import, query, export data in object stores, and use it for fast analytics using table formats like Iceberg and file formats like Parquet.
Hi, my name is Aditya Kumaranchak. I'm a principal engineering architect in the Azure Data product group. So my talk is going to be about migrating very large Oracle databases to Azure Database for PostgreSQL. So if you're a decision maker, or if you're looking to migrate to Azure Postgres, then this talk might be interesting for you.
Hi everyone, my name is Richard Yen. I'm here to talk about PG Stats and about how Postgres and statistics work internally. It's a talk that's geared towards beginner and intermediate users, people who want to get an idea of how Postgres internal statistics operate and how it influences the query planner and how to improve their performance on some of their queries.
Hi, I'm Chun. In this talk, I will share a practical path for getting started with Postgres hacking. And we will look at why Postgres hacking feels differently and how to start small and how small compounds over time. If you are interested in Postgres hacking, then this talk is for you.
Hello, this is Murat Tuncer. I'm going to talk about PostgreSQL authentication, that is from trusted tokens and short history of PostgreSQL authentication. It is about how PostgreSQL authenticates your connection. I'm not going to rank methods, I'm just going to explain why each authentication method exists and how you can choose between them.
Hi, this is Gülçin Yıldırım Yelinek. I do product at Zeta. Today we will talk about what's new in Postgres 18 with constraints. I read all the change log, so you don't need to go through it yourself. And the talk is for everyone who is interested in constraints and app development with Postgres and into also database internals. I hope you will enjoy it.
Hi, I'm Alexander Kukushkin, Principal Engineer at Microsoft. Today I'll talk about PGQ, Postgres extension implementing queue that has been around for almost 20 years. I'll explain why it outperforms keep lock-based design and how to use PGQ on cloud-based Postgres.
The title of this talk is Fast Guard Need Fast Breaks. I guess that's the whole point in one sentence. In our industry, people, tend to go faster. They do want to do things faster, but nobody really talk about breaks. Nobody really talk about the safety mechanism that needs to be built around, getting it faster. And in this talk, I'm going to talk about how to build your safety mechanism when you're building your AI solution.
Hi, my name is Joseph and I want to discuss scaling Postgres multiprocess architecture because it's not just about throwing more hardware at the problem. Each connection carries some hidden tags, and it could be Linux level memory and CPU overhead or Postgres level MVCC and locking constraints. So to manage high performance workloads, we need to understand these limits. So join me for a deep dive into these topics because we shall stop guessing and start tuning our systems.
Hi everyone, I'm Paolo Mecchiore and today I'm talking to you about the Postgres generated column. I'm doing that using some example and using Django ORM and some beautiful picture from Italy to show you how to use this fantastic feature from Postgres and Django.
It was a really good stream. I really enjoyed the panel too, Claire. Yeah. I'm always interested in sort of like that human, the connection to the Postgres project. I mean, how difficult it is that sometimes your patch just doesn't make it, and how do you get over that? How do you deal with that? How do you deal with time zone differences and so on? It was just a really insightful panel. I liked it a lot.
Yeah, the time zones are something that any of us who have teammates across oceans, across continents can identify with. I know I certainly do.
I think that how Melanie put it was like so optimistic that sometimes she would wake up to a review because she had just posted a patch on the mailing list the evening before, and that it was like a present, under the Christmas tree. I thought that was a really nice way of looking at it.
And that is the cup half full side. Like you can go to sleep and wake up and something has happened. And there's been progress while you were sleeping, which is cool. But yeah, then there's okay, I sent it to them and I'm not going to hear back for 36 hours because I sent it right after they went offline or whatever. So it cuts both ways.
Sure.
Yeah, that hackers panel, absolutely worth listening to. If you are a current Postgres contributor, a future one, somebody who's thinking of
aspiring one,
Postgres
yeah,
hacker,
exactly. Yeah.
even people who work on other open source projects as developers. I just think, and those 4 humans are amazing. So yeah, it was a lot of fun. Okay, and speaking of amazing, time for our next speaker introduction.
Yeah, exactly. So Sakshi Nasha is a software engineer who cares deeply about diversity in tech. That really, came forward from her bio. So that's cool to read. Is an open search ambassador, a free and open source software contributor, and an international speaker. And with her talk today, she aims to tackle some common Postgres security oversights in real systems. So I'm excited about a security talk in this live stream. So let's roll.
All right.
Hi everyone, my name is Sakshi Nasha and I'm a software engineer at Cohesity. Today we're going to talk all about security in Postgres. Is your Postgres really secure or is it just working? Are you thinking of security as a design habit or just thinking it as an afterthought after you launch your product? So if you have security in mind and Postgres, this talk is for you. Okay, let's deep dive from dev to prod. How can you secure Postgres the right way? Before we start, I would like to briefly introduce myself. My name is Sakshi Nasha, and as you know, I have been working in Cohesity as a software engineer where I build secure enterprise applications. I've been an open source contributor for more than 5 years now, and I've been contributing to Postgres, OpenSearch, Kubernetes, and a lot of open source applications. And I personally love connecting with people and communities. Until now, I have given 25 plus international talks on topics of Go, APIs, security, Postgres, and many other things to come up. Apart from work, I just love to play badminton, I love hiking and traveling all around the world. Okay, before we just start over right into security in Postgres, I would like to first touch on why does security really matter in Postgres, right? So that's about like, why do we really need this? So most of the organizations these days focus on performance, shipping features first, while security remains a backseat. And it's mostly default driven. So maybe like default public schemas, default auditing, and when a big incident occurs, like when a leak credentials come up or it's misusing of roles, then the first response of many of the organizations is very reactive. And most of the organizations think of security as an afterthought and not as a design habit at all. And that doesn't really work in production grade applications. It should really be a design habit right from the planning phase. So here's the goal. The goal is to shift security from reactive to proactive approach. That is, taking it as a design habit right from the planning phase to not being an afterthought, right? So yeah, that's about it. And let me just walk you through one of the case study where from my past experiences, how I have discovered few security blind spots that defaults that really work under development environment, but they don't really work under production. So let me just walk you through few of the security blind spots that we would like to just give a glimpse about. First of all, the most obvious part here is public schema access. So before Postgres 15, the public schema allowed really broader object creations by default. So if it is left unchanged, like if it is default, then it could really make users or applications create unintended objects. And these unintended objects in turn have a risk for permission misuse. So that's a security blind spot underneath, which can just point out to the default settings. The second one being an overprivileged roles, right? Like many teams use super user for migration, for maintenance workflows. So these super user roles, right, they have weak permission boundaries. By weak permission boundaries, as in like they have more permissions or maybe not the right permissions that are needed for the right job. If in case these overprivileged roles or weak permission boundaries are compromised, that's a big blast radius that's massive, right? And the key rotation, it's just a pain for cloud ops. So that's the first and the foremost thing, is to have the least privilege principle that we're going to cover in future slides. And the third one being, once you have all the roles, everything in place, Then the client-server communication, that's unencrypted, right? That's potentially the third one, missing TLS. So the sensitive data, the queries, the passwords can be easily intercepted, right, at transit, right? So we don't really want our data in unencrypted format, right? So that security is at risk. So the fourth one is when you have default query auditing, or you have low-level query auditing or no query auditing at all. But the default is not capturing the information that you really need. Maybe standard logs aren't enough, which do not give details about who did what, when, was the access suspicious. So all this information, when you really need, it's having a little more than defaults, right? So all these security vulnerabilities create potential risk in production, but in development environment, when the developers just test the code, it really works fine. So let me just walk you through one of the CVEs here that is one of the critical CVE that got exposed in 2025. So in normal cases, when a user inputs the data, the developers often use Postgres functions like the escape string to sanitize the input, right? Before the input is sent to the SQL functions behind the SQL commands, right? So before entering this, it's sanitized, ensuring that the SQL remains safe. But under some edge cases, I mean, like there are misused encoding conditions, right? There are certain misusing encoding conditions. These functions did not fully sanitize or did not fully neutralize the escaping functions, and that really caused the SQL injection. And the mistake the organizations made here was over-reliance over escaping APIs. And over-reliance over escaping APIs caused the manual construction, and they were also relying on client-side safety, right? Like they were assuming that the client side is very safe. So instead of adopting production-grade practices like prepared statements, strict input validation, they were just relying on assumptions. And such vulnerabilities like CVE 2025 makes us remind that production security really depends on layered defenses. And we're going to talk a little more on which layers each by when we progress onto the slides. We'll cover layer by layer how defenses are being formed and not assume that they are in place, right? So that each edge cases like this one here, the encoding edge case, must be checked and not assumed. And to read more about the security vulnerability, you can just scan the QR code to the right. And yeah, that was one of the case study that I wanted to cover. So now that we know why do we really need security as a design habit, and also we know what are the production blind spots, let's now bridge the gap between how organizations and developers can really early on do some things so as to avoid these incidences and make the database really resilient, right? So we'll talk about various rules here, like a layer approach. So the first one being limit your blast radius as much as you can, right? Like following the least privilege principle. So here we just segregate out various roles based on cases. For example, if we have application, which uses migration, which is used for migration schema, or if we have admin roles, then we just define various roles. So in the screenshot, as you can see, I have defined various roles like app read role, app write role, and also I have revoked all the public schemas, right? As Postgres defaults may grant more than necessary permissions, right? And that's not what we really want. We define a clear permission boundary here. And then we can create role based on use cases. Like if we have application specific roles, then we just grant different object schemas there. So that's how we are defining a clear boundary here. And also, just to give you a short tip here, like we must avoid using super user. And this is like if super user is compromised, it's gonna just control the whole database because super user has all the permissions. But like you may ask me that maintenance jobs, some of the workflows in maintenance strictly need super user. Maybe they want to run analyze job, or maybe they want to run the vacuum functions. So they really need super user, right? Then how are we gonna follow this principle? So I'll pause here. I'll not tell you the answer right now, but stay curious until the last slide so that we can cover. There's something in the Postgres enhancements that cover this up. So just to summarize this, we must always keep in mind that every service should have only the permission that it absolutely needs. Absolutely needs as in no more, no less. That's what the basic whole fundamental rule 1 is. So let's just go on to rule number 2 here. Rule number 2, so as Postgres deployment really grow beyond simple applications, role permissions really are not enough, like they're no longer enough for securing your production systems. Schema isolation becomes a real game changer here. When you think of schema changes in production, like in a stronger approach, is to have designing a schema with multiple design, right? Like when you have app, admin, audit, like you can see in the screenshots, I've created schemas for app, I've created schema for admin, I've created schema for audit. So I have created multiple schema design, right? And I have also locked down the public schema to reduce the surface attack. So we have revoked all the public schemas from the defaults, right? So the goal here is to move from convenience-based development, like convenience-based development as in when the defaults are just left like that, or when developers use shared public schemas, right? This is going to work in development, but when you shift to production, they're going to break. And that's going to be a very weak namespace, right? And that's going to increase the attack surface in turn. So we're going to move from convenience-based development patterns into intentional security boundaries. So like that's the rule number 2. So as privileges mode mature, namespace control becomes your next security layer. By namespace control, I mean security in terms of schema isolation, right? So that's rule number 2. Let's go on to what we want to discuss. So just to summarize, we had rule number 1, where we were segregating roles and making specific roles for specific use cases. For rule number 2, we just have different schemas, right? Multiple schema design. Let's go on to rule number 3 now. The rule number 3 is a little different from the standard basic one here. Like while you have schema isolation that protects the structural boundaries, right? Like structure, I mean roles, permissions. The search path is a little different, and that's gonna blow your mind, because most of the production systems, they don't really take this as a security setting. So search path is basically for somebody who is new, who is not aware. Search path is like controls, like it particularly controls how Postgres resolves object names during execution. So if you're calling a function name, from which schema, if you have not defined like schema.function, if you have not defined that, from which schema will this function be called? So that is determined by the search path. And if you don't have the search path setting, right, if it's a very overlooked setting, by default, weak or overly broader search paths configurations are what's the default in Postgres, right? So it really can allow redirection to malicious execution functions, right? Like for example, I'll give you a little low level example here, but we can understand the scope of it in enterprise applications. So for example, there's a function that you can see here that calculates bonus, right? In the public schema, I define this function called bonus. It fetches data. It can fetch data from database, like tell me the current salary of the employee, and then I'm gonna calculate the bonus for it, right? And there's another function that I have created in the admin schema that is grant bonus, and which in turn you can see it's gonna call the calculate bonus, right? And that's calculate bonus is in the public schema, grant bonus is in the admin schema. Here, as you can see, I have one more default, which is security definer. So just to give you a high level overview of what security definer really is, it will execute this function, not like if you are calling from a different schema, grant bonus, it's gonna call this grant bonus not from the caller's privileges, but it's gonna call it from the admin privileges, the definer's privileges, right? So the grant bonus will be called with admin privileges. That's like gonna create a little more schema things. So let me just walk you through how malicious code can be infected here. So let's consider the same functions, right? Now the attacker comes in, it creates exactly same function, like exactly same as in function signature is the same, right? Calculate bonus is the same. It's defined in the public schema. It takes in the input, it returns input, right? So it's the same code, but underneath you're gonna see the select. It's gonna return 10 million bonus amount. I mean, yeah, I wish I could be that hacker so that I could get that much amount of bonus. But yeah, let's switch gears here. Now when this grant bonus is called, right, when with the admin privileges, when the grant bonus is called, it's gonna look at the search path. And if the search path is really weak, it's gonna redirect it. The function call is gonna redirect to the malicious code, the code that was inserted by the hacker, right? So this function execution from the previous calculate bonus, it's gonna call this calculate bonus, right? Because of the search path being very weak, right? The function execution got redirected. And that's not what we really want, right? The best practice in production is to harden this search path. So as you can see, in the later lines here, I have altered the function where I have given the function a specific search path being admin, PG catalog. So I restrict it to not have public schema at all, right? And then we also define qualified object names, right? Like schema.object, right? Like that. And also we define a control definer functions. So as you can see here, I have defined the function that don't let it intended being called from a schema, public schema, right? Just make it call from admin schema, and all of the schemas, just don't let them call this grant bonus function, right? So with these practices, like we control who can execute the function, even with the definer permission, right? And also we control which function should be called by hardening the search path. When you harden the search path, you can really define who calls it and which function can be called, right? So hence, with the control execution path, it's very much essential, right, for having security privilege boundaries. And when I say secure privilege boundaries, it's not just about having right rows, having schema isolation, but also having the search path, the execution path of all the functions being very much defined and controlled. So yeah, I think now that we have covered how to secure the roles, how to secure the permissions, are we really good to deploy the applications in production? Or is the design habit really done? Or are we waiting for some bug to come up, right? So are we really good? I don't think we are really good here. We need one more parameter here, because that's gonna be really a game changer, I feel. So yeah, security does not just go in boundaries or securing the permissions. You need to also secure the data that stays in your database, on your disk, everywhere, right? You need to keep it protected while it's moving across the network as well, right? And so this brings us to really TLS coming up, right? So you need to protect the data in rest, data in transit. So just to give you a glimpse about how we can protect this data. So without TLS, sensitive data such as credentials, queries can be really exposed in transit, right? And at rest, we must really make sure that our encryption is at the right place. Is it encrypting the data? And then is it storing it on the disk in the encrypted format? Are the backups encrypted? So just to analyze this, why do we really want the data to be backed up and stored, right? If there is an infrastructure that is being hacked completely, right? If there's a whole infrastructure that is compromised, then the data that sits in, it's still in the encrypted format, and the data is resilient after all, right? So that's the basic thing of ensuring that our data at rest is safe and resilient. Also, moving on to regular key rotations, right? That is really very, very tedious task for DevOps, to short-lived tokens or maybe workload identity federations where you don't really have to manage any of your credentials, right? So these short-lived tokens reduce the long-time exposure, and that's the main goal, right? Not manage the credentials at all. And there's also one more thing, which is we can avoid using like authentication methods that are legacy, using older password methods, to using Scrum SHA-256. That's really providing a more stronger approach towards authentication. And this one more thing here, which is when you are many of the developers or database administrators really don't take into consideration the configuration file of PG host based authentication, which was like pghba.config. They really don't take this into consideration, like who controls what. All of them is defined, like who can connect, where can it be connected from, what are the security requirements to get connected to this network. All of these is defined in this file. So just to give you one short example here, let's consider if this is the host HBA file, and the first one being host SSL. So host SSL allow only SSL or TLS traffic, right? Only encrypted connections. And apply this rule to all the databases. Apply this rule to all the users, right? And we are also doing an IP whitelisting here. Like as you can see, we are restricting the network range to come only from 10.0.0.0/24, right? So we are restricting those parameters as well. And we are also giving a stronger authentication method here, that is Scrum SHA-256. So all in all, we are just having a stronger security, whitelisting it, allowing connections only from specific SSL connections, and applying it to all the objects in our schema. So that's the fundamental steps for securing data beyond the permissions, beyond schema isolation, beyond privileges, beyond role creation. We also secure the data at rest. We secure the data at transit. Now, let me just give you a glimpse over some of the recent security advancements that went in Postgres 17 and Postgres 18, right? So in Postgres 17, there was a big announcement for maintenance workflows. I hope you remember in one of the slides we discussed we should not give super user, right, as the role for, or we should not grant super user to anybody, right? Then how do we do the maintenance job? So that's when Postgres 17 really made a game changer move here. There are two enhancements that for maintenance workflows that really went through. So in Postgres 17, they added a safer search path that handles really that handles it really in a maintenance workflow, and it reduces the risk from unsafe object manipulation and unsafe function conflicts to really going into a safer search path. So that was the first enhancement that went through for the maintenance jobs. And the second one was they introduced a new role called PG_maintain role, which you can really use for all the maintenance jobs. So maybe if you want to do a vacuum, maybe if you want to analyze, maybe you want to re-index. So for all of these jobs where maintenance usually want to use these functions, they no longer depend or they no longer grant the full super user, right? They really just use the PG maintain role and they're good. So that's when that really changed, right? That we can now follow the least privileged model with Postgres 17 new enhancements. Also in Postgres 17, like I still remember I gave a talk in Postgres Europe last year in Riga, Latvia about incremental backups, right? How we can have incremental backups that supported in Postgres 17. So in Postgres 17, from the basic backup, they moved on to incremental backups that would really support into providing operational resiliency and backup security after all, right? So yeah, you can you can just scan the QR for more updates on what are the other security enhancements that went through for 17, 18, and if you want to give a detailed understanding about it, you can just scan this. For Postgres 18, they introduced the OAuth support. So with this OAuth, you can really integrate external IDPs, right? Maybe SSOs, maybe other federated identities. So you can just include all of these integrated onto these Postgres, right? So yeah, that's about the two major enhancements that I personally think from a security point of view, they are really important and they really changed many of the production grade applications. These were the enhancements that really they clearly prove that Postgres is evolving towards more secure production environments rather than keeping it to defaults. So yeah, I think we've covered most of it. So yeah, just let us move towards how we can move towards the security. Let me just have a checklist, like what all we covered. So firstly, just identify your security blind spots, right? Identify it at the right place and revoke all the unsafe defaults, right? Don't assume anything, right? As we covered in the case study, they assumed that the escaping APIs, the over reliance over them, right, really was a big pain for them. So don't just assume it. Identify your blind spots, revoke all the unsafe defaults. And the 4 rules that we discussed: define the clear permission boundaries by having least privilege model. Then have the namespace control over it so that you have schema isolation. And once you have all of these into place, you also want to have a control execution path. So control execution path can be achieved via hardening the search paths. You also secure the security definer usage, like which schema can call the security definer usage, right? With all of these, you achieve security in the permission boundaries, right? Restricting a clear boundaries. But when you want to move towards beyond data, that is when data at rest or data at transit comes into play, right? So you enforce TLS, you encrypt the data which is stored and also back it up. And also you configure PG-HBA config files, right? So these are some of the tips that I had for covering all of the security parameters. And stay tuned for more PG releases here, right? So yeah, that's all that I had for today. I hope you learned something new, and I hope I have convinced you enough to make security a design habit. And I hope to connect with you. If you have any questions, scan this QR, connect with me on LinkedIn, and I would love to hear your feedback and improve further. Last but not the least, thank you to Postgres, the whole entire team, Linda, Isaac, Corleen, everybody who really made this possible, and they gave me an opportunity to just be here and share my thoughts. Bye. Until next time.
That was a really nice shout out at the end there.
Yeah. And Sakshi, well, it's very kind of her to do that, but she's also not the only one. Like the compliments to the production team behind the scenes, it helped coach people and record people and bring the talks to. It's been really nice, I think, and I think it makes people's days.
So keep them coming, is what you're saying.
Absolutely, keep them coming. And in addition to giving shout outs to the production team or doing the event survey, obviously you can also pass your compliments and your feedback and suggestions on, what could be added in the future to Sakshi, because I know she gives talks in other conferences as well.
Yeah.
So your feedback will probably influence a future version of this, right?
That was a very smooth segue, Claire. I need to tell you.
I try.
Yeah.
Yeah. Hence the espresso. Okay, are we ready to introduce the next talk? Introduce. Okay. I have the pleasure of introducing Shashikant Shakya. He is a Postgres performance engineer who works at Microsoft. He's based in India. And before becoming an architect and a performance specialist, he actually spent years supporting customers, which I think is, I remember a conversation I had with David Rowley once, who's a Postgres committer and hacker. Like, supporting customers is one of the best ways to really build that understanding of people's pain points and their needs and their requirements. And I think it helps no matter what kind of roles you move on to in the course of your career. Shashi's talk here and now today in Posette is about Postgres 18 and vacuum and analyze enhancements. I think something everybody is going to be interested in. So let's roll the video.
Welcome everyone. My name is Shashikant. Today I'm going to talk about what I think is the most exciting area of improvement in PostgreSQL 18, vacuuming. If you ever dealt with the PostgreSQL database in production, whether that's on Azure, on-premise, or anywhere else, the changes which we're going to cover today directly affects how your database handles bloat, freezing, and overall maintenance. Now let's dive into vacuuming enhancement in PostgreSQL 18. What makes it faster, smarter, and more predictable? Before we get into PostgreSQL 18 specific features, let's first understand why vacuuming is so important in PostgreSQL. Vacuuming is a PostgreSQL lifeline. It helps to reclaim the storage from the dead tuple that has been created by the update and leave statement. It also helps to prevent the transaction ID wraparound situation. In case if you've never dealt with this situation, it's one of those emergencies where it can put your database into the read-only state. Part of the vacuum is also analyze, which can keep the query planner stats accurate. That helps in overall faster query executions. When you have a poorly tuned auto vacuum, that can lead to a table bloat, degraded query performance, and it can even lead to a wraparound situation. The wraparound emergencies has been now reduced since the release of PG14. But if someone is not paying attention to their vacuuming cycles on PostgreSQL, this can still happen. PostgreSQL 18 delivers the most significant collection of vacuum and analyze improvements over the years. What we are talking about is the faster I/O, dynamic scaling of auto vacuum workers, smarter way of triggering the auto vacuums on tables, better observability. Now all of this is production ready in PG18. We're going to cover all of these features in more details in upcoming slides. In these slides, what we have is on the left-hand side, what we described is the pain points which we had prior to PG18. And the right-hand, what we have is how PG18 addresses all of these challenges. So before PG18, vacuums were blocks on the synchronous read. So it has to wait for an IO to complete, then wait for the IO to get complete, process it, and then again, redo the same thing. Changing the auto vacuum max worker requires a full server reboot window, which is not even possible for busy production days. There was no hard caps on the dead tuples, so the larger tables accumulate millions of rows in bloat. The normal vacuums were skipping all visible pages, and anti-wraparound vacuums were causing IO storms. And when you had inheritance-based partitioning tables, and you need to manually vacuum and analyze your child tables. Tail truncation in the vacuumings happens silently, which stalls the reads on the replicas. And there was no auto vacuum and the vacuum counters of our specific tables. PG18 addressed all of these pain points with this release. So now you have a new asynchronous IO subsystem, which helps vacuums to read ahead while processing. You can now adjust auto vacuum max workers on the fly without a restart. Now the larger tables can accumulate up to 100 millions of dead rows based on the default settings, and it will trigger an auto vacuum workers immediately afterwards. Eager freezing allow you to spread the freezing activity across all vacuum runs so that it will reduce the IO strengths caused by the anti-wraparound vacuums. Vacuum and analyze on the inheritance-based partitioning tables can now include the partition by defaults. And you have a global settings for controlling the truncation, tail shrinking activity in the vacuuming. And you also have the counters for vacuuming and analyze in pgstat all user tables. Let's start with each one of these features in more details in upcoming slides. We're going to start with the asynchronous IO for vacuum. This is the headline feature release for PostgreSQL 18. And this also helps the vacuuming. It's a game changer for anyone who is dealing with the high latency storage And what I think is in cloud era, most of us are dealing with the similar problems. So prior to PG18, vacuums heap scans were entirely synchronous. It has to request a page from the disk and wait for that IO to get complete, then process it, and then request for the next page. On network storage like Cloud Disk, NFS, SAN, this wait time adds up dramatically. With PG18, now the vacuum heap scan can prefetches the pages where it's currently processing. And while it's working on one set of page, it can request the other set of page from the disk. And this asynchronous IO behavior has been controlled by the two settings. By one of these is IO method by default set to worker, which spawns the dedicated IO workers for doing this work. And then you have IO worker, which has been set to default 3. And if you see your vacuums heap scans are taking longer time in PostgreSQL, then you can think of scaling this IO workers from 3 to 6. And even if you have a larger system, you can go up to 12. So the key takeaway from here is that you get faster vacuums out of the box without making any configuration changes. And the settings are available for you just in case if you wanted to scale further. Now we're going to talk about flexible auto vacuum scaling. This is one of the long-standing pain point every experienced DBA has ran into. So the problem was, let me walk you through this problem. So you have a busy production day, and you are seeing that bloat has been increasing on the tables significantly. And while you looked into the things that you have realized that all of your auto vacuum workers has been working on the large tables. And you need new workers to spin up that can do the further vacuuming activity on your server. To do that, you would require, prior to PG18, you would require a full restart window or maintenance window to do this change, or you could have done this manual work. But with the PG18, now you can dynamically scale your auto vacuum max workers. And how it is done, the auto vacuums gives you the one more setting, which is auto vacuum worker slots. And this setting controls the worker pool, and this has been configured during the startup. So it has been configured as 16. So I don't think you will need a change. You need to make a change after you have these settings enabled by default. And you can only adjust the auto vacuum max workers by default, which is set to 3. You can scale even higher when it's required. You can decrease it when it's not needed. The only thing which you need to keep in mind while you're scaling and descaling the workers is all of these workers have been sharing the same cost limit and delays. So in case if you are making any adjustment to the max workers, you also need to scale the cost limit. If you're scaling higher, you need to also adjust the cost limit so that each worker get the specific cost, and so it can do its works efficiently. Else, if you just keep increasing the workers without making any changes to the cost limits, it's going to slow down the existing workers, and overall vacuum activity on the tables will be slower down. Now we're going to talk about the hard cap on dead tuples. So this is one of the why we didn't have this feature before, kind of a feature. So it's simple change, but it's also a great problem for the large PostgreSQL deployments. So the problem is the auto vacuum has to trigger on a table based on the certain threshold. The dead tuple has to exceed the rel tuples multiplied by the scale factor plus vacuum thresholds. And this has to be, so think that you have a 1 billion rows table with the default auto vacuum setting, which is 20% scale factor. You will require 200 million dead tuples on a table to trigger an auto vacuum. 200 million dead tuples sitting on a table, consuming a lot of storage, slowing down all of your queries. And with PG18, this now gets solved with the new settings, which is like a max ceiling of dead tuples on any of the table. And the parameter called auto vacuum max threshold. This can be set on the instance level. You can set it to conservatively 50 million or lower when you wanted to trigger vacuum faster on your tables. So this This can be even done on the specific tables. You can even disable this for specific tables. So all of these SQL statement here is an example that the way you can do it. Yeah, this is a simple change, but it solves a very great problem of silent bloat on large PostgreSQL deployments. Now we're going to talk about eager freezing. This is one of the long-standing operational headaches for anti-wraparound IO storms. So prior to PG18, the normal vacuums often skip all visible pages, thinking that it doesn't have to clear anything there. But those pages might have unfrozen tuples. And over the period of time, these unfrozen tuples accumulate drastically. And when a server reaches a wraparound thresholds, a PostgreSQL force aggressive vacuum on the aggressive vacuums that scans all pages, including the pages which has been marked as all visible. And these anti-wraparound vacuums are heavy, consume a lot more IO, and can hold resources for extended period of time. With PG18, now the normal vacuums can proactively freeze tuples during the normal runs. And this setting has been controlled by the freeze failure, eager freeze failure rate, which is max eager freeze failure rate, which has been set to by default 3%. This spreads the freezing work across the normal vacuum runs instead of saving it all for a one big IO storm. You can set this on an instance level. You can even set this higher on aggressive tables, hot tables, or you can disable it. So some of the SQL examples are here, how you can do this change. Now we're going to talk about vacuum and analyze recurs by default. So this is one of those quality of life improvements when people are dealing with partitioning tables. And with the size of the data is growing, I think everybody is now dealing with the partitioning, and everybody has experienced dealing with the partitioning. So prior to PG18, inheritance-based partitioning, when you run vacuum analyze on the parent tables, you need to also do the child tables vacuuming separately than the parent tables. And this was an operational headache. You need to build your own scripts to do this. But with the PG18, now inheritance-based partitioning, when you do a vacuum analyze on a parent, it recurs the child tables by default. And if you wanted to fall back to previous behavior, you just want to do the parents vacuuming analyze, you can use the only keywords. So there are examples available in the SQL statements, which you can see how you can do the vacuum or analyze statements. With the declarative partitioning, we have one more twist. Now, when you do the analyze on a parent table for declarative partitioning, it will recurse all the child tables, and which you don't want to do on a busy production day. If you have, let's say, like busy full production day going on, if you just want to analyze this type for parent table, you don't want to go ahead and scan all the child table which has been available. So for that, you have an option of now, like you can only specify analyze only keywords, and it will only scan the parent table stats. Now we're going to talk about vacuum truncate. This is a global setting which has been available in PG18. So this makes the vacuum tail shrinking predictable. And this is the feature needed for the people who deals with read replica workload. So in earlier versions of PostgreSQL, when the auto vacuum finishes the table, it may shrink a tail, which means it may empty the pages from the end of the table storage. This sounds harmless, but it requires an access exclusive lock, which needs to be replayed to the replicas. And if you are using your replicas for the read workload, the reads on the replicas briefly stalled. And these creates a problem for your workload. With the PG18, you can now control this behavior more explicitly by turning this off on the instance level by just changing one switch vacuum_truncate. So this solves a silent problem where the replicas were getting stalled from the primary whenever there is a vacuum activity. And you can turn it off whenever it's needed. You can turn it on whenever it's required. There are ways you can do this on the specific tables. Like you can set this on the off on the tables, or you can set this on the tables. So there are configuration available, or SQL statements are there for as an example to make this change. Now we're going to talk about one of the biggest observability change, which was required for all of the DBAs or the people. They want to have more visibility around the vacuuming areas. So they want to really see where the vacuuming timings are really going. So now you have 4 new counters in the pgstat all tables. So you get the total vacuum time, you get the total auto vacuum time, you get the total analyzed time, total auto analyzed time. So this now enables you to really look into what are the top tables which has been where the vacuum is doing its job. Yeah, so I was talking about the new setting, which was track cost delay timing, right? So this is a new setting which has been available since PG18. And this setting is basically allow you to look into the delay timings of your vacuum progress. So this has been disabled by default for performance reasons. You can, when it's enabled, you can look into pgstat progress vacuums, and you can look for the column delay timings. And you can, with this, you can really fine tune your cost delays for the tables, which has been like taking a lot of time due to the aggressive or the lower cost delay timings. Analyze now can also give you more verbose information of the values, your CPU time and the average read rate. So now it can give you much more insights than just simple telling you that analyze has been completed on a table. There is a new security role improvement also happened, which is PG signal auto vacuum workers. Now it can allow the non-super users to signal the auto vacuum workers, which means you don't have to really give anybody super user privilege to handle the auto vacuums. And this is the quick reference of all the parameters changes with respect to vacuuming in PG18. And some of them are startup parameters, some of them are dynamic parameters. So AIO parameters are common for vacuuming and the normal IO operations. So I'll not go I'll not go list down each and every one. You just so this list is there. You can explore it when you have PG18 deployments. You can explore all of these parameters. The key takeaways. So let me bring it all together here. So we discussed about a lot of good improvements in PG18. So PG18 makes vacuum faster, predictable, and easier to tune. The AIO subsystem helps the vacuuming scale further. And max workers, dynamic scaling of the max workers allow you to take vacuuming control much more granular ways. Earlier it was you have to deal with the maintenance window and taking the restarts and doing it. Hard caps and the eager phasing is enabled by defaults. And explicit tail shrinking now has a better control, and you have better observability. And so net effect is like you get a smoother auto vacuum, shorter aggressive vacuums, and fewer locks on your application, fewer locks for your application workloads. Some of the resources and the references which has been, I've kept it here. These has been helped me to build this presentation for you. So this is one of my blog which has been written recently, PG18 vacuuming improvement explained. So this has much more details about each feature, what we have talked about here. Then you also have PostgreSQL 18 release notes. Then we have vacuuming documentation. Then we also have auto vacuum tuning. This is one of our go-to doc when you're dealing with the auto vacuum issues in PostgreSQL. And thank you all. Thank you for your time. And now I'm happy to take questions. All of you can reach out to me on LinkedIn. My LinkedIn link is there on the slides. And you can also refer to my blog, PG18 Vacuuming, for more details. And thank you.
Alrighty, super. I'm actually hoping that the link to that blog post will be posted in the Discord as well, so we can read it.
Yeah, well, hopefully your wish is a command and it's going to happen momentarily. So let's see how that works out. Because people are in the Discord. And so you just have to go to aka.ms, open -source-discord. And even if you're watching this live stream, tomorrow or over the weekend as a replay or something like that, you can scroll back and read the whole conversation from Livestream 4 and all the previous ones too. Sometimes that can be amusing. So, there would be latency involved, but it still might be good. Anyway, you can ask speakers questions now. And survey link, we're putting it up after each talk. So there you go. If you want to give survey feedback on any previous live streams, you just use where it says LS4 at the end, replace it with a 3 or a 2 or a 1. Hopefully that's kind of obvious. Okay. Next introduction.
Yeah, that's me again, Claire. I want to introduce Mohammed Usama, who is a principal software engineer at Microsoft and a major contributor to PGPool 2, an open source project. He's been actively involved with Postgres since 2006, so that's been a while. And in this talk, he'll provide a minimal mental model of how Citus distributes data and explain why cluster scaling can feel slow. So attendees, you all listening on this live stream will learn how to reason about scaling time, plus get an actionable guidance for running scale out, scale in events safely. So let's roll the video.
Hi, I'm Mohammed Usama, and I'm going to talk about Citus cluster scaling. The recent version of Citus landed 2 new enhancements in this area, and I'm going to talk about both of these, how you can leverage those and what they are all about. Okay, so let's get started. The title is Move Less, Move Faster. 2 halves to the title, and I hope by the end of this talk, you'll understand exactly what each one means, and more importantly, why putting them together changes how you scale up Citus cluster, and what benefits do you get from these. Why this talk? So there was a customer of ours, I'll spare you the name, runs a 4-worker Citus cluster and about 18 to 20 terabytes of data. All was good, healthy cluster, happy customer. Then they decided, why don't we add another worker node? So they provisioned a new node line and start rebalancing on a Friday night and went home. Monday morning when they came back, rebalance was still running, and Monday evening it was still running, and finishes sometimes in the Tuesday. Now, if you think like 18 to 20 terabyte is really modern on a modern hardware is nothing. Like it would have taken like few hours max or a day max, but for Citus it took like 3 or 4 days. And so the question is, where the time go? Definitely, the data was not a bottleneck. The machinery that moves the data was the bottleneck. And this talk is what we did to get rid of this issue. Okay, so here's the overview of the talk. The talk consists of 3 parts. The first one is move faster. The second one is move less. And then in the third part, I'm gonna put these all both together, and we're gonna see how you can utilize this. What are the knobs you need to change? What are the options you have? And okay, let's move on with the talk then. Before anything, let's start with a quick Citus refresher in case you only heard about Citus on a coffee break or something, and you do not know, or yeah, you heard the name, but you do not know what it is all about. So in the nutshell, Citus is a Postgres extension, and that turns Postgres into a horizontal scalable cluster. As you can see in the diagram, there is a coordinator at the top, which is just a normal standard Postgres with a Citus extension on it, and then there are n workers, and again, all these workers are simple Postgres with Citus extension. Basically, Citus is a huge extension, but there are 3 main concepts to keep in the mind, and the first one is the distributed tables. So the distributed tables are sharded across all the worker nodes, and then the second one is the reference table. Again, that's a small lookup table, or I should say, it should be a small lookup table, but Yeah, they are tables which has exactly one shard, and they are copied across all the nodes, like exact same copy. They are replicated across all the nodes. And the final one, co-location groups. So the co-location group is a set of distributed table that shares the same distributed column, and their shard lives together on each node. The reason to have these reference table is our co-located group is to make sure our joins works, speed up the joins. Okay, right. So before we discuss the scaling and related improvements, let's quickly look at what scaling actually means in terms of the Citus cluster, of course. Otherwise, everybody knows what the scaling is. So when you add a new worker node to a Citus cluster, that worker node is pretty much empty at the start. And we need to put that node to work by moving some of the shards from other nodes to that new worker node. To do that, Citus run a rebalancer. The purpose of the rebalancer is to move 1 over n shards from all the cluster to that new node, or to that new empty node, you can say. Yeah, that's what rebalancer. Under the hood, the rebalancer does 3 main things. First, it copies all the reference tables to the new worker nodes. As I said, like reference table has to be replicated on all the nodes. And then it moves 1 over n. N is the number of nodes. 1 over n distributed tables to the shard. And finally, a cutover step that flips the placement metadata and drops the old shard placement and old shard data from the old node and mark that placement that it's now present on the new node. So that's pretty much what the rebalancer is. Okay, so that was a quick walkthrough of Citus, just a very, very brief intro about it. So now let's move to the first part. The first part is about making the rebalancer parallel, and this is about moving fast. If you have to move fast. This is the anatomy of a slow rebalancer. Let's see where the time went in our customer's rebalancer job case that I told you about. It took 3 or 4 days to complete. So almost about a quarter of the time, if you see the first 25%, a quarter of the time it was taken by the reference table copy, and the rest of the 70% was taken to moving the shards from the existing nodes to the new node. The 5% is again just like miscellaneous things like creating the constraints and metadata cleanups and stuff. That's not matters. And guess what? Like when this all was happening, the network, the CPU, they were mostly idle. The wall sender of the Postgres, only one was busy at the time, and rest of them ideal. So they have the pretty much all the system resources, yet like Citus was not utilizing it and utilizing those. So that one rebalancer job took like 100 hours maybe. So okay. So why was it serial? So why all the shard and the reference tables move in serial fashion? Like, what is the reason behind it? So there are actually 3 main reasons. First, the first one is a very conservative locking. Actually conflicts the locking which we take to move the shard. It technically conflicts with all other operations on this particular shard or on this particular co-location group. So that's the first reason why the all the rebalancer thing, like all the shard movement, this was serial. And the second was within the co-location group, shard moves sequentially as well. And again, partially because of locking and partially because of design. And the last one was the reference table copy ran inside a single transaction on a single connection. So as part of enabling a 2 parallel rebalancer, we need to fix each of these underlying issues with the existing rebalancer approach. So let's move on to this. Okay, the fix number 1. It is about moving reference tables in parallel. And we need to copy reference table to a new node before we can start moving any distributed shards to that node. And the reason for that is we can have constraints on reference table, like your distributed table could have foreign key or other constraints on the reference table, because the reference table exists on all nodes, so you can have these constraints. Second, like the reference tables could have their constraints within themselves as well. For example, I have two reference tables, they could be connected to each other by foreign key and or maybe or some other constraints as well. So the first step of setting up any node or rebalancing is to move the reference table, and then after that we'll start moving the actual shards or the distributed table shards. But moving the reference table in parallel is not easy, because again, as I told you, like these reference table could be interdependent on each other. So how we achieve the parallelism to move the reference table in parallel? So to achieve that, we actually divide this thing into two steps. First, we're gonna copy the data of the reference tables all in parallel, and then defer the constraint creation for the later step. So once all the reference table, for example, if I have 5 reference table, I'm copying all in parallel, and once all the 5 reference tables are already on the other node, then we start creating the constraints. And so yeah, this is the first fix which we did to kind of parallelize the overall rebalancer. And in case you're thinking why moving reference table in parallel matters, because reference table is supposed to be small, but the reference table are actually small in documentation, but in actual world they tends to be bigger. I have seen reference table like 40 GB, 50 GB each. So yeah, parallelize moving the reference table is a real beneficial for overall performance of the rebalancer. Okay. So the second fix. Once the reference table move bottleneck was removed, the next fix was to fix the locking issues or bottleneck, the over conservative locking we talked about. So the first thing was we set up the goal. What is the goal? What we want to achieve? So basically, we have two kinds of operations in Citus, on a collocation group or on a what you can say distributed table. One is the structural changes, like shard split, promote a clone, create a new distributed table, or changing the layout or changing the schema. So these are kind of a structural changes that that is allowed on the distributed table. And these structural changes must remain serialized against the shard move. So you do not want this like you're doing a structural change and moving a shard at the same time. So that's pretty much not a good idea. And the second type of operations are placement move operations, like shard move, shard copy, which we do it for the rebalancer. And so we should allow these multiple such operations on a different shard to happen in parallel. So they should not conflict with each other. The problem with the existing rebalancer was like it was treating both of these kind of operation as the same kind in the same way, and it was using over conservative logs to block. So if any of the structural change operation or the data move operation was going on, it will the other one will get blocked. So this was the first fix we want to do. And so how did we do that? So this is a table which shows like what changes we made to the logs. So this is I'm not gonna go into the detail of each and every log. So but the overall idea was to remove the overarching logs that serialize the independent moves, and use a log mode that are not self-conflicting for the moves, while they should be conflicting with the other operation, with the structural operation. So that's what we did. And the takeaway was like serialize the dangerous case, yet let the independent shard moves run in parallel. So this was about the locking improvement which we did. So after these locking improvements, so this is the net effect. Like the move. Now we can have two moves run in parallel. Like you can move shard 1, shard 2 in parallel, and even if both of these shards are belonging to the same co-location group, and again, the shard belonging to different co-location groups were allowed, somewhat allowed in previously, but now not. But yeah, we have enhanced that too as well. But at the same time, while we want to block the DDL changes, so in the end, the bottom line is the same operations are still mutually exclusive when they need to be. And the only thing we allow as part of this change is to move versus move. Like that should not be conflicting. And this is exactly what is required for the rebalancer. So now let's come to the third fix. Like the third one was this is the last piece of the puzzle. Like with the logs fix, with the rebalancer, and like we can now move that reference table in parallel as well. So the last thing is to orchestrate all of this. So what we do is like we copy the reference table in parallel, and then once all the reference tables are copied, we apply the constraint. And once the constraint part is done, that means all the reference tables are already on the new worker node. Then we start moving the shards in parallel. So the part is like the Citus already have this background task framework. We didn't, like, as part of this new enhancement, we didn't build it. So the only thing which we did is like smarter scheduling, like so that like we achieve the best throughput out of it. Okay, so again, like for this parallel rebalance, we haven't added any new UDF. Same Citus rebalance start UDF, which is listed in the slide. It now accepts two new optional parameters: parallel transfer collocated shards and parallel transfer reference tables. Right? These are two new arguments which is now allowed in this UDF, and I think they are self-explanatory. And by default, they are off. So like so you do not get any surprise if after upgrading to the latest version, and just in case, flip this off on when you actually need it. Yeah, before I move to the next part, so a word about shard transfer mode. Okay, so why I want to discuss is basically shard transfer mode, the same UDF which we discussed in the last slide. It also accepts the shard transfer mode argument, and it can have either force logical or the logical or the block, right? So these are two types of arguments that it can get. And the force logical is the one that after copying the initial data, do a catch up via logical replication before making a cutover. The good thing about this mode is, mode is writes stay online. Like the writes on the source shard is not blocked for almost the whole move, only for the very small cutover time that they gets blocked. And on the flip side, the replica identity is required on the tables if you want to use this force logical mode. And the second one is the block writes. As the name suggests, on the other hand, like it blocks all the write operations on the source shard until the whole of the shard is copied to the destination. The reason I want to mention this is like the force logical mode, the first one mentioned in the slide, is where the new locking helps the most, primarily because the locking fixes the area and the logic which is used by replication for the shard replication setup for moving the shard in the logical manner. And the block write also have this the benefit, but the benchmark, like the internal benchmark which we did, was like at least 26 to 30% improvement when we are using the force logical to move the shards between the older version and the new Citus version. So let's talk about what actually gets faster and where the wins come from. So if you look at the timeline on the slide, the top bar is the old behavior reference tables, one after another, then shard moves and one at a time. And the bottom shows the new behavior reference tables, overlaps, overlap and multiple shard moves run side by side. So three things drive the vein in this. First, the reference table copy is now one pass per reference table in parallel. The more reference tables you have, the bigger the relative veins are. And second is the distributed shard moves run in parallel across co-location groups. Again, as soon as more than one move can run in parallel, you start gaining the time. And although the constraint and the cleanup, which I mentioned, like they are done in the serial, but still they take a very small amount of time. So the major chunk of the time is gained by parallel moving of reference table and the shards of distributed tables. Okay, so this is the thing. Like, parallelism is again not free, and there's a point past which adding more executors stop helping, and maybe sometime it degrades the performance. And so this is a very important thing to keep in mind. So what if you see this curve, like why it plateaued or flats on after some times. So the thing is, so the bigger the data set gets, the parallel is and you have more parallel workers moving the data. So there comes a time when it's the CPU or the network, they started to become bottleneck. So before that point, like, you keep gaining the performance benefits, but once disk or CPU or network, these things started to become a bottleneck, then there's a possibility like you start seeing a degraded performance, or at least the plateaued performance. So you need to be careful, like how much parallel workers your setup can take or should have. Okay, so before moving to the next part, let's talk about some caveats. Like, if you have one giant shard that dominates the wall time, the parallelism would not help. And as you know, like each move adds a wall sender, a decoder, and a replication slot, or wall sender CPUs. So you need to check, like, what's your max wall sender setting, max replication slots and setting. And again, you have to keep in mind, like, how much of these your system resources can support. Again, so this is the second point. And one more catch is the locking sign. Logical moves only works on the table with the replica identity. So enabling the replica identity means, like, more walls get generated. And so again, though you get a big win with the replica identity, again, that's a trade-off you get from the setting the replica identity on any table. And finally, I think, if your network gets saturated, like, then yeah, you're not gonna get performance. Or even, like, you may start getting the performance for your rebalancer, but you start hurting the regular workload performance. So all these things, like, do keep the headroom for max connection and other settings, and carefully configure these. Okay, so now let's move to the second part, which is move less. We have just done with the move fast part. Now the second part is about the move less. Move less. So if you see, like, if you want how the data is moved by the Citus, how Citus move data is, like, it selects the table one row at a time, and sends that single row again one row at a time to the destination. And this is a Postgres spread. Like, you cannot help it. Like, so because, like, the file has all the tuples, but again, there could be dead tuples in there. There could be non-visible tuples in there. So all we can do is, like, we can run a sequential scan on a table, and then send every row on the other side. But if you step back and you can look, like there is another way to send the data on the other side on the new node, and that is a PG based backup or a disk snapshot or a physical copy. Like you can take a physical copy of the data directory and then you can just ship it over to the new network. But that does not work as it is. Like you cannot like kind of ask Citus to do that, like read the file from the data directory and then just ship it over to the other. So there are two ways to like kind of send the data on the on the worker side. One is Postgres speed, and other is a disk network or the network speed. So this is what the second thing. Yes, like this is the replica to the worker. So the idea is rather than sending one row at a time, why can't we just take the backup of the existing worker and then restore that backup to start a new worker? So by doing this, what we can do is like rather than starting a new worker starting as an empty slate or a blank server, it starts with a replica of the existing worker node. And this is what the life cycle of the worker looks like. And this is about the second feature which we added, which is like adding node using a snapshot of the existing node. So it is the first step is you get a replica of the worker, and you can take it like you use take the replica from using 4 ways. You might use the existing HA replica, you can use existing stored base backup, or you can take a new backup on the fly, or you can just take a disk snapshot. Once you have this restored on the machine, just the second thing you need to do is Citus add clone node. This is a UDF which attaches that replica of the worker to the Citus. And once that is done, the third is pretty much optional step, which is get snapshot based node split plan. So it just gives you the plan. We're going to discuss it in the next slide, like how the plan looks like. And once all these things are done, just call this Citus promote and clone and rebalance UDF, and it will make this the replica as a new primary. So this slide discussed what is done in this the last UDF we talked about in the last slide, Citus promote, clone, and rebalance. So this UDF has 6 steps. The first one is it takes exclusive lock on the source worker, and it blocks all the writes on that worker. And reason it needs to do that is to make sure that the replica it catches up with the source worker node. And but yeah, that is a very small time. Like if you just taken a backup, it could be just matter of few seconds. That's about it. So once the replica or the clone, which we call it in the Citus term, which catched up with the original primary, the next thing it does is it promotes the replica to become using PG promote. It becomes a new primary server. And once that is done, the fifth step is flip the metadata switch. What that means is it marks this clone as a new worker node. Like now the previously added clone becomes a worker node for the Citus, and the last step is rebalance. We're gonna discuss the rebalance. So this is the rebalance. Previously, if you remember what we were doing in the rebalance, we were moving the shards from the existing workers to the new worker, which was taking quite a lot of time. Now what we do is, because we started with a clone which is an exact copy of the existing worker, for example, in the first like S1, S2, S3, S4, like these shards exist on both source and the clone, and they're exactly the same copy, because we made sure just before anything that the clone is not lagging behind. So instead of copying, now we are deleting the shard. So we're gonna delete S3 and S4 from the source, and S1 and S2 from the clone. So now just by dropping and deleting the shards, we did the rebalance. So this is very fast. And this is just an example of like what the snapshot plan gives you the output. So when you call the get snapshot based node split plan between primary and the clone, it gives you which shard will stay on the primary node and which will be moved to the clone node. And once you execute it, shards which is supposed to be staying on the original primary will be deleted from the clone, and the other ones will be deleted from the primary node. Again, this is just what I just described. This is some visual representation of difference between the traditional and the snapshot based node addition, like how they are both different. In the first one, the traditional one, we are moving the shard. We are starting with from an empty node, and we are moving the data from the existing workers to the new one. But with this new snapshot based node addition, what we are doing is we are starting with the clone of the node rather than the empty node, and then we are deleting. So the second one is very fast. I'm just running out of time, so I'm gonna jump to the last part, which is very just a very single or 2 slide long. So which is how we can utilize these two, like pick the right approach. So this is if you're adding the capacity and you already have the H replica, even if you don't have the H replica but you have the large data set, just go with a snapshot based split rather than doing a empty node, starting with the empty node and doing a rebalance. And if you are adding a capacity and with the data set is very small, or you need to drain a node or like then a parallel rebalance is a good. But if you're going to double the number of node, like going from 4 to 8 nodes in, and you have a very small maintenance window, like the only option is go with the snapshot based node addition for the heavy lifting, and eventually do the parallel rebalance. So yeah, these are just operational guidelines. I think we've just already discussed about these. Like these are the knobs like max background task executors and max share pool. These are the things which really affects the performance of parallel rebalance, and you need to be aware of these, and you may need to find your own sweet spot for each of these settings. And in the end, like it's just for the snap. Like if you want to see like how going from 4 to 8 workers, what is the playbook? This is it. Like these are the 6 steps. Take the backup, add it as a clone, get the snapshot plan, review it, do this, and then just call the Citus rebalance start, and then drop the replicant slot in the end just to clean up the things. And yeah, that's about it. Thank you very much.
Super.
You know, Citus talks are near and dear to my heart because it was working at Citus Data that first got me involved in the Postgres community. So I owe a big debt of gratitude to people on the Citus team.
Yeah, and our next speaker, Jimmy, in Discord was calling for more online content around Citus. So maybe that's feedback for next year, Claire.
Yes, for sure. So Jimmy Angelakos, it's my honor to introduce him. And so I should probably move the slides forward before I do that introduction. There's the survey link that I want everyone to see. You know, the year that Boris Mejias was one of the hosts here on the Discord and on the live streams, he made a little contest, right? Where he was saying, hey, I've done this many surveys so far. And he was challenging all of the other hosts to try to keep up with him. And there was a whole competition going on, but we've not been competing this year. It's not a competition.
I'm filling out a talk survey as we go. So, you know, like I'm happy to turn it into a challenge if you want. If you want me to, Claire.
No, I don't want you to. Okay, let me do the introduction for Jimmy Angelakos' talk. So Jimmy works at PG Edge. He's been working in the Postgres project and community for many, many years. He's based in Scotland. He's the founder of a very recently created Edinburgh Postgres user group. He's an extension developer, and he's the author of a popular book called Postgres Mistakes and How to Avoid Them, which seems like a very practical title. And people are enjoying it. It just came out, it feels like a year and a half ago, but it could be 2 years already. Time kind of flies by. He serves on the Postgres Europe Diversity Committee as well. And if we go back in time at Posette 2 years ago, Floor, you and Jimmy were co-speakers on a talk called How to Work with Other People.
Yeah.
And it was about neurodiversity and how we can make space for people whose minds and brains work differently, right? And I don't know, I thought it was really valuable because it's not just about the technology. Like, you want to move a project forward and make it more successful. It's not just about working with code. It's about working with people. So I was glad you guys gave that talk.
And I know that I speak for Jimmy as well. We were super grateful for Posette giving us the stage to talk about this too.
It's an important topic. But this year, his topic is completely different. And he's got a little pun in it. And if you watch the talk, pay attention, you'll quickly see what the pun is if you haven't figured it out already. But it's titled, Listen Carefully How Notify Can Trip Up Your Database. Let's roll.
Hi there. My name is Jimmy Angelakos, and my talk is titled, Listen Carefully How Notify Can Trip Up Your Database. And it is a real-world story. It's a thing that happened in production once upon a time, and it's a real pitfall and situation that can be caused when using this mechanism in Postgres. So I think it's really useful to talk about it and show you what it can cause and also how it can be fixed. So let's get started. Listen carefully how notify can trip up your database. And we'll see exactly what this cryptic sentence means during the talk. So I'm Jimmy Angelakos. I work at PG Edge. I'm based in Edinburgh in Scotland. I've been involved in the open source community for over 25 years, and I'm honored to be named a Postgres significant contributor to the project. I'm a member of the Postgres Europe Diversity Committee, and I've written a couple of books, PostgreSQL Mistakes and How to Avoid Them, and I've co-written the Postgres 16 Administration Cookbook. I've also created a Postgres extension for the visualization and time series analysis of Postgres internal statistics called PGStatViz. So let's see what this talk is about. Listen Notify is a feature that is really elegant, it's powerful, and it also has a trap. So because this is a real world story that happened in the wild, we'll see how we stepped in that trap, how we found out that we had stepped in it, and also how we fixed it. So let's see what Listen Notify is about in Postgres. The use case for these two commands, listen and notify, is to send asynchronous notifications. And usually that's useful in conjunction with an application that acts as the client to your database. So what is exactly the use case? It's letting parts of the application communicate with each other and with the database. So it's what we call inter-process communication, or IPC. What's great about this mechanism, Listen Notify, is that it's built into Postgres. It's really lightweight, and it requires zero extra infrastructure, which, for a fan of the KISS philosophy, such as myself, is amazing, because you don't need to depend on external things such as Redis, Kafka, RabbitMQ, all these other message buses or data buses. You just need to use SQL. So it sounds really awesome. So let's see, how does it work? So internally, it's simple inter-process communication. Postgres, after all, is a multi-process system, and the pattern for Listen Notify is publisher and subscriber. So you just do it the other way around. You start listening as a subscriber, and then you send the notifications as the publisher. It can send messages for payloads that are up to 8 kilobytes, 8,000 bytes actually. This is configurable at compile time. So it's not a hard limit. You can make Postgres send bigger payloads if you roll your own. And additionally, it's transaction safe. This is a mechanism that is transaction aware. So the notifications for your transaction are delivered if the transaction commits. And this is what makes it really safe. Because if you want to notify a third party, such as your application, that something happened in the database definitively, that it was committed in the database, then you send a notification. If that action has indeed succeeded and the transaction is committed, then the notification gets sent. So that's a lot of theory. Let's see how exactly we can do it. So how you use it is there is session A, let's say, that is listening on a channel. So it's announcing that I'm now subscribing to this channel. So listen, order was watchers JSON is my example. So now session A is listening on the channel that's called order watchers JSON. Session B is the publisher in this case. So it's saying, tell this channel that something happened. So it's running notify order watchers JSON, the channel, and then a payload, which in this case is a JSON payload as a string, which is order ID 42 and status is completed, which is what the listener is waiting for. The payload is the information that they want to get notified about asynchronously. And session A indeed receives from this channel order watchers JSON, the payload, and that is 100% it. That's exactly how it works, and it's as simple as that. Now, let us see what happens when you put this in production. So this production setup that we're going to be talking about is a Postgres trigger that contains the notify, and then that notification goes to a legacy application, and that legacy application then puts the message on Redis, and because that's where the newer components of the system are. So the newer components are connected to Redis. The legacy app is also connected to Redis. The legacy app has the database, and therefore when something happens to the database, the legacy app is notified, and it also can tell Redis, so the newer parts of the system can know about this notification, this event. And notify, exactly what it does is it tells the legacy application that a transaction was committed. Now, it is worth mentioning that since this system was put in place, there was a significant increase in customer traffic. So we'll see why that is important. Because with the increase in customer traffic, people started noticing a few symptoms. One day, the worst of the symptoms was there was a sudden spike in canceling statement due to lock timeout log lines. So in the logs, they would see things like this, which were quite unusual to see. So this signified that there was a lock cascade and that the transactions were stalling at commit time. The consequence of that is that errors started appearing on database servers that were really busy. And because things were erroring out or delaying, the client requests had increased wait times, which we can see in the monitoring. So it was really necessary that something was done about this. We needed to investigate why this was happening, because the environments that we had with high transaction volume on the system were starting to suffer from this. So, pull the logs. What did the logs show? The logs showed things like process this acquired access exclusive lock on object 0 of class pub62 of database 0 after 1100 milliseconds. And then another log line and another and another. So they looked exactly like this, the errors that we saw in the log. So the processes were waiting over 1.1 seconds at that point just to obtain a lock. But what is that lock? What is object 0 of class pub62 of database 0? It obviously was not a row lock, and it wasn't a table lock. So we found out that class 1262 was the PG database system catalog. What? Why was something attempting to lock the global database catalog for every single transaction? So this is where the trap was, and the trap is serialization. What do we mean? So to guarantee the ordering of these notifications, every single commit that had a notify call pending required to obtain an access exclusive lock on this global object. And what is another way to say guaranteeing the order of something? It's serialization. So what are the implications here? The implications are that because we were putting notify inside of our trigger, this means that we were forcing transactions that were in reality concurrent to queue one behind another, because the order of the notify calls needed to be guaranteed as commit order. So we effectively invented accidental serialization. Something that should be concurrent and parallel was actually happening one thing at a time. The mistake was that whoever wrote that code initially treated listen and notify as a concurrent message bus, where in reality it wasn't, because Postgres treats listen notify like a globally serialized queue of notifications. And when you're trying to parallelize and do concurrent stuff, that is not the way to do it, because every transaction commit triggered a notification. So as we were seeing more and more customers committing transactions, we had more commits as a volume of commits that were competing for the same global lock. This means that we were artificially restricting our throughput. And as we saw, errors started appearing because the database started killing transactions that waited for too long to obtain this lock because of the lock timeout settings on the production server. So how do you fix something like that? We started exploring solutions. Our first instinct was to just fix it in the application. The problem was that the application, as I said, was a legacy app, and nobody wanted to take the risk of changing something that had been stable and immobile for years. Basically, nobody wanted to touch the legacy application. Don't touch it because it will break. It's a classic development pattern that we see out in the field. And secondly, the solution would have been too complicated because we would have had to create some asynchronous process that was listening for these things asynchronously and not blocking the database and so on. So it turns out that wasn't the right solution, our first instinct. So then we started thinking, can we solve this from the databases side so that we can avoid touching the application? So the problem we're trying to solve is that the notification sending is coupled to the transaction committing. And this is what we need to tackle. So how did I solve this entirely from the database side? First of all, we changed the triggers. Instead of sending a notification, the triggers would write that notification into a notification queue table. This means that they didn't need to obtain any global lock because the trigger was just writing to a separate table. Secondly, the notify function that was sending the notifications needed to grab what we call an advisory lock to ensure that there is only one sender at a time. Remember, we don't want contention on this global notify lock on the database table, on the database catalog. So the third thing is, after you have obtained this lock within this trigger function, you send the notifications that have queued up to that point. And let's see what this means. That the decoupled notification operation is now asynchronous because transactions are unblocked immediately. If they cannot obtain the lock to send the notification, then they're not waiting on it. They're giving up on it immediately. The notification is queued in the table. It remains for the next transaction to pick it up. So what does this notification queue table look like? It was an unlocked table. Why? Because the storage of notifications is ephemeral, right? We don't need it to be crash safe. It's something that needs to notify systems in near real time. So the storage there is temporary, but a temp table isn't good enough. We want an unlocked table because we don't want the churn within this table to affect the write-ahead log. So this doesn't create any bloat because unlocked tables don't go through the wall. So the table looked like order.notification queue. It's a timestamp. The default, because we didn't need to set it explicitly, we set it to be the clock timestamp of the server at that moment in time. And the payload is just text. Now, the changes that we made to the trigger. So by queuing, it means that we no longer call PG notify directly, but instead we insert this JSON payload into the queue. And the trigger function now contains payload, JSON build object, whatever. This is a simplified version of the real world thing that we were sending. Then it checks. If payload is not null, then insert into the notification queue the payload. And it's as simple as that. Now, the next step in the trigger is updating it to do the advisory lock stuff. So after having queued the notification, we attempt to obtain an advisory lock. And this advisory lock only needs to be transaction level. It doesn't need to be global across the system. And it is non-blocking for the rest of the operations. That's why it's called an advisory lock. It's something we want to control. So it tries to do lock acquired equals PG try advisory transaction lock. It obtains an advisory transaction lock for the lock ID that we've hard-coded, and then it checks. If we have indeed obtained this lock, then send the notifications. Otherwise, do nothing and just commit as normal. So we found out the cutoff. We generally don't want to send notifications that are older than 10 seconds. Of course, there's no point. We need this to be almost real time. And so continuing on from that point in the function, we see that we're looping over the notification queue while deleting. And I love this Postgres feature. You can say delete from the table where pstamp is less than 10 seconds, returning star. And this star feeds into the next select, which is select n payload pstamp from notification from notifs n, where n timestamp is greater than the cutoff, so only newer notifications ordered by timestamp. Now we have fetched the notifications from the notification queue table, and we just loop over them and send them in a batch. So we perform now that we have the lock, and we know that there's no one else who can obtain this advisory lock and try to send notifications at the same time. We do a perform PG notify to our channel, the payload, and that's the entirety of the loop. These are the relevant parts of the function. The logic, the business logic is not relevant in this case. So how does this fix work? In practice, the transactions that fail to obtain the lock instantaneously, they simply commit. The queued notifications are picked up by the a transaction in the future that managed to get the lock. This means that PG notify, as a consequence, was not contented because there's only one sender at any moment in time. So there's only one short lock held for PG notify for the entire batch. How did we test this? And you should test everything and trust nothing, including your own code. We tested this for correctness, concurrency. We tested for race conditions that could arise because we changed the queuing logic of the whole application/database interaction. We tested it for performance, regressions in case it broke something, on a clone of the production database that had a synchronous standby. Why? We needed a synchronous standby because that's what production had, to introduce a realistic commit latency, because commits don't happen instantly when you have a synchronous standby. You need to do the round trip to make sure that it has been committed somewhere else. And then we stress tested 4 times the transaction volume that we were seeing in production at that moment in time, which is great because we got great results. We sustained the rate of 4 times the production volume on a database instance that was actually smaller than production. So that's a good thing. But because I said trust nothing, we also had logging. So right after the insert statement, I put in a little thing that would report the queue length in the database logs just so that we could keep an eye on it. So this code reports the queue length in about 0.5% of all transactions for logging purposes. I chose the modulo of 199 because 199 is a prime number, so it's unlikely that we would end up in a bad pattern of exactly 100, 200 batch and so on. So if the current transaction modulo 199, then we just set the logger verbosity to, because we just want to output this single line that raises a warning that says order notification queue length. And then in order to avoid selecting from the notification queue table, we would just do a pgstat get live tuples for that table, which reports almost exactly the size of this table. And then we need to exit the state of logger verbosity. We would just reset it. The results that we got was we saw an immediate difference. The log timeout errors disappeared in production, and in our stress tests, we had transactions throughput that more than tripled compared to the old code. So now the performance was again bound by the hardware instead of our self-induced bottlenecks that our code had. So the client requests saw reduced wait times, and that's a good thing. So to recap all of this, Listen Notify is a powerful and elegant feature that Postgres includes. However, it can become a silent bottleneck when you have high concurrency and high throughput systems. So watch out for these kinds of things, global locks, especially if they are in a high frequency trigger that gets triggered hundreds of times a second. Advisory locks are awesome. You can use them for manual concurrency control, which is what we did here. We didn't want two callers to send notifications concurrently, and we fixed that. The bottom line is you should keep Notify out of your hot path in whatever your application happens to be. So thank you very much for listening. This is a topic close to my heart, mistakes you can make with Postgres, and that's why I wrote a book. You can get a discount with this code on the book or any other product on manning.com. And I will now join the Discord to answer any of your questions. Thank you so much for listening.
Super, and I appreciate the discount code for the book too.
Well, and one of the things you can do with whether you're watching the talk video on YouTube or watching the live stream is, and I like that versus in person. In person is great, but I like being able to pause and stop, get that QR code. You know what I mean? Like get the screenshot. I do not own Jimmy's book. So maybe
Well-
I should take advantage of this.
Listen, I just heard of a great offer, you know?
All right. Well, thank you very much, Jimmy, for that talk. We have, is it just one more talk? Oh, obviously
It's just
survey
one
links.
more, yeah.
Deadline for surveys, Monday, 22 June, 11:59 p.m. Anywhere on Earth time zone, anywhere on Earth. But yeah, this is our final, but not last but not least is the phrase we use in English. One more talk to go.
Yeah, okay. Well, let's enjoy that last talk then, even extra, I guess. So Hamid Akhtar is a senior software engineer at Microsoft who's specialized in Postgres' internals and in large-scale data replication. And through this talk, we'll gain a little bit, like look behind the scenes. We're tracing a complete lifecycle of one tuple as it travels through Postgres' logical replication pipeline. Because, it's one thing if a thing works, but it's a different thing entirely if you understand how it works. So I'm looking forward to this deep dive. Let's go.
All right.
Hello, everyone. My name is Hamid Akhtar, and today I'm going to talk about where does my insert go, a logical replication story. In this talk, we're going to start with an insert from the publisher to the subscriber database. So if you're planning on understanding the workflow of how logical replication works, this talk is for you. It will give you all the details about the wall, the logical replication, the decoding, and take you from the publisher to the subscriber. Okay, so where does my insert go? Time to look into more detail now. So here is the roadmap. On the left-hand side, you see 3 stops. On the right-hand side, you see 3 more stops. The left-hand side is really all about how a tuple is actually being written on the publisher. We start from the insert, the time the insert begins on the publisher, makes its way to the shared buffer, eventually to the wall, And how does adding, say, or changing the wall level to logical adds more detail to it? And finally, how does the publishing work? Starts with logical decoding layer. The reorder buffer comes in, which reassembles the transaction order. And then finally, to the next three stops, the replication slots and the output plugins, and finally the subscriber receiving that data. So to understand this, we're essentially going to walk through all of these 9 stops, understanding what exactly is done at each stop, and then we're going to make our way towards the publisher and the subscriber towards the end. So the story begins when we receive an insert statement. In our case, as you see on the slide, insert into orders a customer ID and the amount. It's a pretty big amount, as you can see, $99.95. So what exactly happens here? Obviously, the Postgres or the publisher in this case receives this query. It goes through the parsing and analyzing and rewriting phases and the planning phase, which eventually generates an optimized query tree, which is passed to the executor. The executor in this particular case is now going to insert that query or the tuple data. But before it can do that, it needs to construct a structure which is essentially a representation of a row of that particular table, in our case, the orders table. So we're going to see that the column and the values that we provided in the insert statements are going to be transformed into something that Postgres or the table representation can understand. So it starts with some information about the header, which is essentially the visibility information and the placement information and certain flags that define the state of that tuple. So xmin is the transaction ID of the transaction that's creating this tuple. Then there's some meta information about it, the null bitmaps and the actual column data. So xmax, obviously in this case, being an insert statement, is 0 because xmax represents the transaction ID that deletes or removes or updates that tuple. So now at the end of this first phase or the first stop, we now have a representation of a row as a tuple. So it's a heap tuple in this case, which is the standard Postgres table format. Now what we need to do is insert this tuple into the table itself. But before we can do that, we need to essentially find a space in that table. That table can have spaces in any of its blocks where our tuple can fit in, or maybe there is a requirement to extend that relation so that we can, if there's not enough space in the table. That's where the free space map comes in. So our tuple finds a place on the 42nd page of this table. This 42nd page represents the blocks in the shared buffer. Shared buffer is the memory that's shared across all the backends. So the part of heap insert process ends up taking an exclusive block on that buffer, putting that tuple data in there, and making sure that the line pointer or a kind of a position holder marking where the tuple starts is updated so that within that block we can find that tuple conveniently. So after the second stop, we have that data in the table in memory in our shared buffer. It's not persistent yet. So the table headers are updated, but still it's not crash safe yet. So we next need to create a wall record here. A wall record represents the write-ahead log record that ensures durability of this tuple. So this all should happen before we can confirm to the client or to the user that the data has been saved successfully and the transaction has committed successfully. So what happens here? We start with xlog begin insert, telling the xlog that we're actually intending to write something here and add a wall record. So
Once we do that, we then insert some metadata. We insert the tuple data into it, and we assemble that wall record in memory right now. Why in memory? Because so far we've not committed the transaction, so there's no way of us basically saying that this transaction is good to go. So the wall can be flushed either at specific, say, the intervals by the background writer for wall, or through a commit statement. When we issue a commit statement, that's when the xlog data is actually flushed onto the disk, and that's the first time when this insert or this tuple is actually guaranteed to survive a crash. So we now have our transaction committed. We now have a tuple that's durable, that's in wall, and that is crash safe. So the anatomy of that wall record actually has some other details in it. It has information about the transaction ID. It has the information about what's known as a resource manager and some information about it. A resource manager identifies what or how or who interprets this wall record. So in our case, it's the resource manager is heap. It knows, for example, certain operations or how to interpret certain wall records. So, and now based on that data, it can understand as part of, say, xlog info that this is an insert statement for a heap. So now it can interpret that, and it can actually understand or update other aspects with it. The important thing to note here is that in the wall, we don't just write the data of that tuple. In some cases, in case full page image writes is on, which by default is, we might dump the whole page or the whole 8K block to the wall. That is to prevent, again, certain crashes, which is like, for example, a torn page, which, say, as we're writing an 8K page to the disk, we might end up crashing midway. So just writing 4K rather than 8K. So this full page image writes will protect us against those torn pages. So far, we've created a tuple. We've saved that in memory in shared buffer. We've saved that in the wall data, and we've preserved that on disk. But for us now, we need to interpret that data as column and values. There are different types of wall levels that we can set. A replica is essentially to replicate data that's in binary format, but without any specific knowledge of what that data represents. So if we've set up streaming replication, all we need to know is what data should we update. We don't care what columns or what values there are. We don't need to understand that information. All we need to know is this chunk goes where, and that's what we do. So if it's an 8K chunk, the entire block, we replace the entire block. If it's the tuple data, we replace that tuple data in that block, in that place. That's all done as part of streaming replication or physical replication. But for logical replication, we also need to understand that data so that we can deal with it smartly, because we need to understand from a logical perspective what columns were updated, what were their values in this particular case. So if we are inserting a tuple, we need to understand the columns and their values specifically and the relation that it was part of. So there's certain additional pieces of information that are added when logical replication, for logical replication. So we have the origin information that prevents cycles. We have some markers telling the logical replication pipeline that we have new tuple as part of this data, so it can then decode it. We also need to make sure that when we're doing full page image writes, we're not actually overwriting, or we're still carrying that tuple data with it. So in physical replication, when we're doing a full page image write, we don't preserve the data for that tuple. that we've just inserted. But in logical replication, we need to logically interpret that, and therefore we need that information, additional piece of information along with it. We additionally might need some information about the relation. We might need additional information whether this transaction committed or aborted, and we might need some information about the catalogs. So in the logical decoding layer involves a wall sender process, logical decoding, and reorder buffer. Now, these are three pretty intense components of logical replication. Starting with wall sender, a wall sender gets initiated when a subscriber connects. So it's initiated by the subscriber when the postmaster receives a request to start replication, and a wall sender is launched. The wall sender is responsible for reading the wall data. It's essentially sleeping on a latch or waiting for more data to arrive, more wall data to arrive. When some wall data is generated, it's these wall senders that are waiting for that particular kind of wall are woken up. So you have separate for streaming replication and then separate wall senders for logical replication. They're woken up when their corresponding data becomes available. So they wake up, and that's when the processing starts. So remember that as part of wall writing, we added additional information for it to be logically decoded. That's not there for streaming replication. So the wall sender starts and it'll initiate the logical decoder process. But then becomes another challenge. The wall is not written sequentially it's written sequentially, but it's not contiguous for a commit. It may or may not be. So we'll come to that and see how that happens or why that happens. So what happens here is that when the wall sender sees that there's more wall for it to receive, it reads that wall, and then it finally sees that, oh, so this wall can be processed by this particular resource manager, RM heap in this case, and it knows that it has additional information about how that resource manager should interpret that particular wall record, which is provided in Excel or Xlog info. So it's an insert in our case. So it invokes the resource manager for heap, giving it the wall record and the info. So what happens particularly with wall? On the left-hand side, you can see that the wall is actually interleaved. You have multiple running transactions. They're doing DMLs. They're doing inserts, updates, and deletes. And they're running in parallel. So there's no way of us holding back one particular backend for another while it completes a transaction and writes all the wall contents onto disk. So the changes, the DMLs are interleaved. So on the left-hand side, you can see that you have transaction A, it performs an insert, transaction B performs an insert, transaction A performs an update, and transaction B commits. Finally, transaction A commits. Although transaction A started earlier, it commits later. Obviously, when reading the wall sender now needs to make sure that it can interpret all of this data accurately, and that's where the transaction ID that was inserted as part of the wall record comes in handy. So we have the resource manager, we have the transaction ID. So as it's reading those wall records, it's organizing that data in transaction IDs based on their transaction ID. So it's grouping them together. So that's what reorder buffer does. It's going to reorder the wall stream based on the transaction ID. And within those transaction IDs, if there are sub-transaction IDs, it's also going to put them under the parent transaction ID. So you see that it's collected transaction B first, insert and commit, not transaction A, which started earlier. it's done with transaction B first, and then it's going to basically process transaction A. So more about the reorder buffer. It's, as you can see, what it does is that it creates a list essentially based on transaction ID. And it's going to put everything, all the wall record, all the changes within that wall record under that transaction ID key. That's the organization. So the moment it receives that information, it's going to put all of that information in memory, in its buffer, and it's going to wait for a transaction boundary to come. Whether that's a commit, whether that's a rollback, that will come as the process proceeds on, as we receive more wall. So, but it's doing that simultaneously, or it's doing that in parallel, not waiting for the transaction boundary and then collecting all the wall records, but it's doing that along the way as the transactions are in progress. So how or what happens internally is that it's collecting all that pieces of information, it's collecting all those changes, it's making sure that it's the moment more wall arrives, it understands which transaction it belongs to and puts that change under that transaction as a part of that structure. So the heap decode processes is going to create those reorder buffer changes, and it's a list. It's basically a queue, a process where you have all those changes. But at this point, we're not sure whether this transaction committed or aborted. And it's all being done while the transaction is in progress. So finally, or eventually, when the xlog exec commit arrives, and that's the xlog info that can be handled by your transaction resource manager, it now then invokes the function exec decode. Now that's part of the resource manager callback function array. So the wall sender receives this commit, and now basically it's going to go through with the decoding process. It calls decode commit, registers all the sub-transactions, it reorganizes all the sub-transactions because the sub-transactions also need to be organized or put into the LSN order. The LSN is the log sequence number for the wall, basically the position of that wall record within the stream of wall, so that the changes are replayed in that very same sequence rather than out of sequence. So the reorder buffer is responsible for collecting all those changes. It's also then, in case of transaction commit, is responsible for shipping out those changes to whoever is listening on. The reorder buffer then essentially is going to invoke the decoders, the logical decoders for it, to process those changes. But it can suffer from certain issues with work mem, where if there's a very large transaction, it might end up writing to disk, it might end up costing significant I/O. So that's one caveat where you have large transactions that may cause this issue. But the protocol for logical decoding provides you with a streaming option where you can stream those changes across to the standby, to the subscriber, without waiting for a commit or a rollback record. So what happens is that once we receive a commit, we know that we need to send out this change to the subscriber. That's different from a physical replication setup. So it's basically going to start with begin callback. It's going to provide certain information there. And then for each change that it has collected in the reorder buffer, it's going to send out a change callback or call the change callback for the logical decoder output plugin. And finally, when the commit is received, it is going to send out the commit. So it detects a commit. It, for all the sub-transactions, is going to do a k-way merge. trying to not sort, but organize or pick up the lowest LSN values for all the sub-transactions and send them one by one. So it's not going to look at or sending out all the sub-transactions in one go, but see which change came in first. So you can see the signature, what the signature of an output plugin begin callback would be, where the XID is provided, the commit timestamp is provided, and that information is sent out to the subscriber. Then for each change, it's going to do a change callback where it's going to provide that information about that particular change. In our case, it's the insert into the public orders table and the corresponding data. And finally, when we reach the commit in the reorder buffer, we're going to send the XID and the commit LSN. The replication slots are there to ensure that the subscribers' data that they rely on the publisher is preserved. So the wall segments are preserved. They're not lost because for the wall cleanup policy kicks in. So they are basically your guarantee to the for logical replication that would ensure that the LSNs that are still required, the wall records that are still required by the subscriber are retained on the publisher. Yes, it can lead to significant growth in the wall data, but that's the trade-off. If a subscriber needs it and the subscriber is actively utilizing it, you would not have that issue. But the subscriber really relies on the restart LSN, which tracks, say, the catalog changes that may be required. The confirm flush LSN is the point where the subscriber has made changes durable that it's received from the publisher. So the output plugins that are part of the logical decoding flow are the standard one is PG output. You have a test decoding that you can use or understand or test in a human readable format, the output of this logical replication. And then there's a third party wall to JSON, which can be utilized by third parties or by CDC pipelines. Here is their output in simplified format. So test decoding, you can see it's clearly in a human readable format. Wall to JSON is obviously in a JSON format, which can be machine processed or by another software. And then you have PG output, which is going through the protocol for binary protocol for logical replication with a begin message, relation information, which carries the information about the OID of that relation, the columns, its data types, and everything that you need to know about that relation. Insert message, in case of update, you would have old and new values, and the commit message finally. So that's your protocol for output. On the apply side, we're receiving these protocol messages from the publisher with begin. So on the subscriber, we end up creating a subscriber transaction. We start receiving all the changes, then we apply those changes locally. And remember, these are not binary changes. These are logical changes. So we receive the table name, the column, and the value. So we're making those changes ourselves by applying those heap changes ourselves here. So we end up making that change in the orders table. We commit it locally, and after that's committed, we update the REPL origin LSN, which is then sent back to the publisher, telling it that this is the LSN that we have made durable on the subscriber. So our tuple started with a SQL statement. The heap tuple made its way into the memory, then to physical wall record, then as part of a logical decoding change. Finally, it made its way to the logical or the reorder buffer queue to the output plugin, which then decoded the ordered reorder buffer and sent messages to the subscriber, and finally the subscriber implementing those changes on its side. So the complete set of stops that we have are insert statements, the executor, which creates the heap tuple, the shared buffer, which is the table in memory essentially, or part of that in memory, the wall buffers, the wall on disk, the wall sender that performs the decoder process or initiates it, the reorder buffer, which organizes your commit and all the changes in a set, the replication slot, which ensures that the data that is required by the subscriber is not lost on the publisher. The output plugin sends out the changes to the subscriber, and the apply on the subscriber applies those changes. So we have the physical path, which is really the executor and the buffer and the wall. The logical path, which is decoding, reorder buffer, and output plugin. The wall level, which adds additional information. Reorder buffer, which organizes all the wall records and emits them in the order so that it can be committed in that in an LSN sequence order. Replication slots ensures guarantee that no changes are lost. Output plugin is basically an extension, an extensibility layer, which by default provides logical replication. And obviously, like in most observability issues, long-running transactions would be a challenge, would hold back a lot of this process. That's all. So thank you so much. Here is my contact information, and you can also find me in the Discord channel in case you have any questions. I know this has been a lot of details, a lot of information, so feel free to reach out to me in the Discord channel. Thank you.
Wow.
Alrighty. Super. With all of those steps, it reminded me of a previous talk with the Ticket to Ride reference, you know, like it felt like we're on another journey like that again here.
There's a lot to learn from here, and I'm glad I'm going to be able to watch some of these talks again on YouTube. And sometimes I watch talks at 1.5x speed or 2x speed, and sometimes I got to slow them down. All right. Well, you know what? We usually it's time for the wrap up at the end of one of these live streams, and we've got like 25 minutes to chit chat. But today in this live stream floor, you and I do not have 25 minutes to chit chat. I do want everyone to know that the talk survey links and the event survey links are there. I popped them up again. If you've been here the whole time, you're like, oh my gosh, we know. Stop saying this. But we also know that some people pop in and out, and they then go back and watch things later. So what's next after live stream 4?
Well, I mean, the Discord is still alive and kicking, so you can definitely still hop in there and chat some more. And also after the event, of course, because you know the open source Microsoft Discord is always on, so you can always join that and connect with people. Did we talk about feedback? I'm not sure we talked about feedback, Claire. Feedback is a gift. Make sure that you give generously. And of course, like all the talks will be available both as the live streams and as individual talks, so you can play those back.
Yeah, if you go to that playlist right now, this very second live, you're actually going to see a link to last year's playlist, because we're not going to publish these talks until after you and I get off the live stream. So there's a little bit of latency, but not much. So shortly afterwards, you'll find them there. And then, so after live stream 4 is over, you can go to that playlist. You can find all 44 talks. We'll also be publishing a playlist that has all 4 live streams. So if you do want to do a replay or have a watch party like you were describing with Peter Eisentraut, that may be a way to do it. The videos that get published online are going to have those high quality captions and translations, which should be useful. I know that on the Discord, in one of the previous live streams, somebody was saying that they were participating in the stream, but they had the volume on silent to avoid waking up their partner. And so they were relying on the captions to understand what was being said. So
I also love the dedication to just continue streaming. Yeah, good.
There you go. Again, thank you to all the speakers. We would not be here. There would not be all this great learning. In one of the talks, I think it was yesterday, somebody said that Postgres has survived and thrived all these 30 years without a marketing department. I mean, there are people in the community who spend time on advocacy. So maybe it's not fair to say there's not a marketing department. There are press releases and there's a ton of documentation and release notes. But the fact is that the whole community does a lot of training, does a lot of teaching. And so props to all these speakers. Definitely. We've got how many minutes for a wrap? All right. Want to go fast, Floor?
Yeah, let's do fast. Sure. Let's go.
Okay. We've already talked about Discord.
We talked about the 11 talks that we had that were all great.
We
No
watched the
types.
11 talks.
Yeah.
We've talked about where to find everything after Livestream 4 is over. If you haven't had a chance to see the keynote, particularly if you're an Azure database customer and you're really curious about what's happening with Postgres at Microsoft, Afon's and Charles's keynote should be super interesting to you. And if you're a hacker or someone in the Postgres open source community, you're probably going to be interested in this keynote, which is focused on like what's in Postgres 19 and what made it and what didn't make it. And yeah.
And also, I it was definitely one of my highlights of Posette this year, because what a fun group of people together in a panel, and amazing insights of what it means to be a Postgres committer, contributor. So yeah, definitely recommend everyone to check this one out.
And shout out to Daniel Gustafson, because he helped me conceive of the idea for this panel before we went and invited everybody. And he actually helped with the invitations as well. So it wouldn't have happened without him in the background too.
Well, thank you, Daniel, because great stuff.
Thank you. Okay, so all these different talk surveys, obviously, if you want to give feedback on something from Livestream 1, you have to use a slightly different AKA URL to get there. The QR codes are here as well. You can always find this live stream on YouTube. So you can go find the QR codes even tomorrow or Sunday or something like that. If you do that, there's an opportunity to get the socks and the stickers both. Just make sure you submit by that Monday, the 22nd, 11:59 p.m. anywhere on Earth. Anybody's eligible to get the sticker swag. Just hop on into the Discord, click on the links, submit your address and your shipping information. We did it.
We did do it. Yeah, really good. Thank you also, Claire, for inviting me this year to this live stream with you. It's always a pleasure, and it's just such a pleasure to be with you and with everyone backstage and do this show.
Well, I appreciate how you very much do your homework, right? Watching the talks in advance, figuring out what you want to focus on and highlight. It's so cool. There are upcoming in-person events. So we've got a few on here, including one that Floor is involved with. Swiss PG Days coming up, I think, next week or the week after, near the end of June. Hyderabad PG Days in August. PG Day UK in September. Lowlands. Is that the second most popular conference in Europe?
Second best Postgres conference in Europe is our official marketing slogan. There you go.
BFP is still open for PG Down Under. We've got Postgres Summit US, formerly PGConf New York City, PGConf EU in Valencia, Spain. So lots to look forward to in the in-person conference circuit. Podcast. Go check out talkingpostgres.com. Lots of great Postgres conversations. We covered this earlier if you were here. And there's something called the Azure Developer Hub. I want to say that anyone who's an app dev who runs on Azure and is looking for like a one-stop shop to find training and tooling and just links to things that can sometimes seem fragmented, this hub should be super useful to you. And so go check it out. And then thank you again. Just a bit of gratitude before we wrap. This conference is organized by a lot of people who did a whole bunch of hard work at Microsoft. So thank you to the Postgres team at Microsoft. And this year we did it in partnership with AMD. So I want to say thank you to AMD for their support as well this year. And talk selection team, the organizing team. There's just a lot.
Keep on coming.
The live stream hosts, there's a lot going on. It's like the credits rolling at the end of a movie. If you don't know what a gaffer is, you don't know what a gaffer is, but it's important. So thank you, everybody. And thank you, Floor.
Thank you so much.
Ciao.
I had a blast.
I did too.